సార్ స్ట్రీమ్ యూట్యూబ్ స్ట్రీమ్ పంపించారా? సురేష్ సార్, సురేష్
సార్ పంపించిన.
ఓకే. ప్రోగ్రామ్ సురేష్ సార్, ప్రోగ్రామ్ షెడ్యూల్ డిస్ప్లే ఒకసారి మళ్ళీ రిటర్న్ చేస్తాను.
స్లైడ్ పెట్టిరు
ఇప్పుడు ఉన్నదా? దీని తర్వాత
స్లైడ్ ఉంది.
ఓకే ఓకే. సార్ అరౌండ్ సార్ 870 రిజిస్ట్రేషన్స్ అయినాయి సార్. అంటే ఇంకా మేము ముందే స్టాప్ చేసాం సార్ 2 days బిఫోర్. అట్లీస్ట్ వీఆర్ ఎక్స్పెక్టింగ్ హాఫ్ ఆఫ్ ద స్ట్రెంత్ టుడే ప్రెసెంట్. నేను కూడా ఎక్స్పెక్ట్ చేయలేదు సార్, అరౌండ్ 200-300 వస్తారు అనుకున్నా, కానీ విత్ ఇన్ 3 days ఇట్ క్రాస్ ద 600. సో 800 తర్వాత ఇక మేమే క్లోజ్ చేసాం సార్. సో ఓవరాల్గా all faculty throughout India, sir, around 600 faculty members are registered because of CAC, IT and maths together, sir. So speakers lo kuda sir, one of the speaker is a BOS nominee sir for us university. Okay. Gaudan sir ani inko aina ma junior sir. Swamidas sir kuda one of the speaker for cyber security oka session తీసుకుంటాను sir, oka 1 hour.
ఓకే. రాజన్న లైవ్ స్ట్రీమ్ ఉందన్న?
ఓకే ఓకే. మేడం జాయిన్ అవుతున్నాను సార్ ఇప్పుడు ఒక అదే సార్.
Suresh sir, something disturbance background.
So video వస్తలే సురేష్. సురేష్
చెక్ చేస్తున్నాను.
వీడియో వస్తలేదు నాది.
మీరు వీడియో క్లిక్ చేయండి మీది.
అదే వస్తలేదు ఇది వస్తలేదని చూడు. You cannot stay your video because the host has stopped it. Host stopped అని వస్తుంది.
ఒక్క నిమిషం. ఇప్పుడు చూడండి అన్న.
ఇప్పుడు వచ్చింది.
మీరే వీడియో ఆఫ్ చేసుకోండి. నేను ఆఫ్ చేస్తే మళ్ళీ నేను ఇవ్వాల్సి వస్తుంది.
అదే ఊరికే ఆన్ ఆఫ్ అవుతుంది అది. నేను
మీరే ఆఫ్ చేసుకోవాలి అది వీడియోలో.
ఓకే రైట్.
Sir, good morning, Principal Sir.
Good morning, madam. Rajreddy garu, Madam Jain, you can start.
Good morning, madam. Suresh. Suresh sir. Suresh.
సార్ చెప్పండి.
ప్రోగ్రామ్ స్టార్ట్ చేయండి. శారదా మేడం రెడీ ఉన్నది కదా?
శారదా మేడం రెడీ.
Okay. Shall I start, sir?
Yes, madam.
Good morning, one and all. A warm welcome to the one-day online seminar on application of number theory and cryptography, organized by Department of Mathematics, CBIT. I am Dr. K. Sharda, Assistant Professor, Department of Mathematics, CBIT. Now, I take privilege of welcoming the dignitaries, Srimati D. Sandeshri Garu. She is a member, chairperson, DNP of Chaitanya Bharati Educational Society. She holds a master's degree in architecture from School of Planning and Architecture, New Delhi. Also, she is the managing director of Frontiers Design Group since 1990. Apart from her own consultancy in architecture, interiors and landscape, she also has been the advisor and consultant to the governments of Telangana and Andhra Pradesh for development of urban scapes. Thank you, ma'am. Your motivation and support strengthen the institution. Now, I would like to welcome the honorable guest, Professor P. Ravindra Reddy Garu. He is the principal, CBIT. He served the institution as the Dean R&D, Professor, Head of the Department of Mechanical Engineering. He has 31 years of vast experience in teaching, industrial and research areas. He was a chief and principal investigator for 23 research and 37 industrial consultancy projects. He has guided 22 PhD scholars and published 6 patents. He has published over 310 research papers in reputed international journals and conferences and organized 27 workshops and FDPs and delivered 135 keynote and invited talks. Also, he received many awards such as UGC Fellowship Award in 2000, Excellence A grade by AICTE for the Monroe Project in 2003, Engineer of the Year by the Government of AP and IIE in 2004, Distinguished Leader Award by Venus International Foundation in 2019. Also, he is very active in professional societies. Thank you, sir. Your encouragement and care improved your academic standards. Now, I would like to introduce Professor P. Rajireddy Garu. He is a HOD, Department of Mathematics. He completed his MSc and PhD from Usmania University in Mathematics and MTech from IETE in Computer Science. He has 22 years of experience in UG and PG. He has published 25 research papers in national and international journals and presented 50 papers in national or international conferences and workshops. Also, he is active in professional bodies and life member in IETE, APSMS, TSSMS. Thank you, sir. Thank you for your support to the department. Thank you, sir. Now I request Suresh sir to play the invocation song.
మేడం మీరే ప్లే చేయండి.
Okay.
कुन्देन्दु तुषारहार धवला या शुभ्रवस्त्रान्विता या वीणां वरदण्डमण्डितकरा या श्वेत पद्मासना या ब्रह्माच्युत शङ्कर प्रभृतिभिर्देवैः सदा पूजिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा।
Thank you. Now, welcome address by our principal. So now I request our principal, sir, just to speak a few words. Over to you, sir.
Good morning, all of you. Respected Srimati D. Sandhasri Garu, Chairperson DNP member BOM CBIT, Dr. P. Rajireddy Garu, Head of Mathematics Department, Dr. V. Srinivas Garu, Speaker of today's morning session, colleagues and participants. I welcome you all for the inaugural of one-day online national seminar on application of number theory and cryptography. Chaitanya Bharati Institute of Technology started in the year 1979. with the 3 programs. Now it has grown to number of programs in UG around 9 and PG 10, that includes engineering, technology, and management MCA. Altogether, we have 5,125 students, and this year we are adding 3 more UG programs in computer science, engineering with artificial and machine learning, data science, and IoT applications. And one more MTech program in artificial intelligence data science, which is altogether we can have 5,300 students on campus. To take care of these students, we have 600 both faculty as well the supporting staff on campus. We are very thankful to our management, Dr. Malakunda Reddy Garu, President CBIT, and Madam Sundasri Garu, all other board members for the development of the institute to take care of all the students, teaching, learning, research, collaboration, consultancy. And CBIT is NAC accredited from 2013 onwards and autonomous. It became autonomous in 2013, and second cycle it's going on. All our UG programs are accredited by NBA. And we have the teaching, learning, research, collaboration in a greater extent. This year, our faculty submitted almost 131 research projects to various supporting and sponsoring agencies. We are hoping that getting such a research projects and people can work, both the students and faculty, in these areas. When it comes to the today's program, the Department of Mathematics is organizing a number theory and cryptography, which is very required at this stage. And as we know, even number theory is a very classical discipline in mathematics, has been studied so long. And it is a study of relations among the integers. Cryptography is the art of the secretly transmitting informatics, and it is as old as people trying to hide their secrets. I think the deliberations for today may be on elementary number theory and finite fields and quadratic residues primarily, and factoring. Then crypto systems, we know the crypto kinds are so famous, and people are around the crypto kinds. And we have various applications like electronic commerce, then the chip-based payments parts, digital currencies that most of the people knows, the computer passwords, and the military communications where this cryptography is being used, and number theory also. So though I'm a mechanical engineering, I enjoy mathematics. So really all the participants can interact very well with all the speakers, and the program is very well defined by the department. I congratulate the mathematics department, my colleagues, Dr. Raja Reddy, head of the department, all other colleagues for taking part and initiating this one-day online national seminar. Thank you very much for giving this opportunity.
Thank you. Now, I would like to call the convener of today's seminar, Dr. P. Reddy Garu, to speak few words about the seminar and the department.
Respected Madam Sundasri Garu, Board Member, Chairperson DNP, Principal Dr. P. Reddy Garu, CBIT, my colleague Dr. M. Ganesha Rao, Professor of Mathematics and one of the conveners for this program. My junior colleague Dr. P.Suresh, Assistant Professor Senior, co-convener for this program. Good morning, one and all. A warm welcome to all of you. We are overwhelmed by the response received from the faculty, research scholars, and students from various parts of the country, and we are happy to inform you that around 850 participants have registered for this national seminar. The today national seminar on application of number theory and cryptography consists of 5 sessions from 9:30 a.m. to 4:30 p.m. I sincerely thank the guest speakers of today, Dr. C. Govardhan, Usman University, Dr. Srinivas from Usman University, Dr. Swami Das, our beloved professors of the CBIT, for taking their valuable time to deliver the lectures. About the department. The Department of Maths currently has the 12 faculty members who have vast research interest in different domains of mathematics and allied sciences, such as fluid mechanics, number theory, fixed point theory, and operational research. I am proud to say that all 11 out of 12 faculty members are PhD holders, and the remaining one faculty is pursuing PhD in applied mathematics. So far, department had published 250 papers in various reputed national and international level. Around 350 papers were presented in various national and international conferences, and around 10 training programs were conducted by the Department of Mathematics. As we know, number theory and its application play an important role in encryption and decryption algorithms. Cryptography is the practice of techniques for secure communication to preserve the data and integrate the data and confidentiality. For instance, the economic imbalance in the society during the COVID-19 crisis, hacking has become predominant in the field of banking sector, defense sector, and telecom sector. So the above mentioned problems can be tackled with the help of application of number theory and cryptography, which forms the basis of a cybersecurity. Finally, I believe today's lectures by our distinguished speakers will be highly informative, knowledgeable, and thought-provoking to all our participants. Thank you.
Thank you, sir. Now, I request Srimati D. Sandeshri ma'am got present. Speak few words about this seminar.
Good morning, everyone, and welcome to our one-day national webinar on applications of number theory and cryptography. And I'm thanking speakers of today's webinar for accepting our invitation. And I'll just inform about our college students. It's a very important information for mathematics faculty. They're all scared of mathematics. I don't know why. They are all, in the sense, more than 50%, and which is not needed. In fact, what they feel, physics, chemistry, because many times I speak to these first year students and second year, whenever I meet them in the corridors, though I don't know them, I'll just ask few questions. So most of the students are scared of mathematics, and they're also not willing to, get into mathematics. Most of them, I mean, more than 50%. See, they all feel physics and chemistry are all right, but why math after intermediate? But I feel we have to prepare a kind of lecture explaining the use of mathematics in various streams of engineering. And it should be graphical, pictorial, to create some kind of interest in them, and the importance of mathematics, without which they cannot become engineers. In every electronic transaction, we have cryptography. See, all these in the first year itself, in the orientation time, if we can explain about mathematics, because physics and chemistry, they are very sure of, they are okay with it, but they are very innocent. So this particular thing I wanted to always inform, but this is the platform where I am able to speak to all of you. So one of you can take this as a nice lecture, and it should be properly presented to these first years. This is my suggestion, and I wish the entire team grand success and thorough learning experience for all our participants. And the last word, stay home and stay safe, because you all know what is the pandemic, corona, is doing outside. So take all precautions and suspect all, and also at the same time we have to respect all. And thanks one and all.
Thank you, madam. Thank you for your inspirational words and importance of mathematics. And also I would like to thank Principal Sir for his valuable information about our esteemed institution and the department. Thank you, one and all. Now, I request Dr. Mamta Thakur to start the first session of today's event. Over to you, madam.
Good morning and a warm welcome to one and all. I am Dr. Mamta Thakur from the Department of Mathematics. I take immense pleasure in introducing the speaker of this session, Dr. V. Srinivas. Dr. V. Srinivas from the Department of Mathematics, Usmania University College of Science, Saifabad, is a doctorate in mathematics with specialization in fixed point theory. He has 58 publications to his credit at national and international level. Under his guidance, 2 PhDs have been awarded and presently 6 scholars are pursuing their research. With his today's talk on number theory, we all wish to enlighten ourselves. Now I invite Dr. V. Srinivas sir to deliver his talk. Over to you, sir.
A very good morning to all of you. This gives me a great pleasure to associate myself in this August gathering, that too sitting at homes. So at the outset, I would like to thank the management, head of the department, principal of CBIT college for inviting me to deliver a lecture on number theory and its applications. Today, I am going to deliver a lecture for 2 sessions. At present scenario, number theory got much importance to students, budding engineering, scientists, and researchers. So because of its beauty, so much research is going on at various places. You know, cryptography means that is the sending of message in secret manner between a sender and receiver. The original message is called a plain text. That plain text will be sent to the receiver. The process of sending that message is called encryption. Further, that will be decrypted and it will be retrieved by the sender himself. And in the process of using cryptography, so many mathematics techniques are involved. Actually, they are very much used. To mention a few, which I am going to deliver today, namely division algorithm, Euclidean algorithm, primal testing, solution of congruences and their applications, Euler-Tauschent function and its properties, Fermat theorem, Euler's theorem, and Chinese remainder theorem. And even more, some of the topics, they are needed even from algebra, like finite fields. So with this small introduction, I would like to conclude my speech, and I congratulate all the participants and I wish them the best of luck in their future endeavors. I hope this lecture will enthrall all the audience. Thank you, one and all.
Sir will continue the lecture, sir.
Okay, so today I am going to continue 2 sessions. In the first session, I am starting with fundamentals.
Suresh sir, phone.
I hope it is visible to all.
Yes, sir.
Okay. So,
Full
my
screen,
lecture.
sir. Thank you, sir.
Sir, I used, right.
So my lecture starts with some discussions on number theory. So already I motivated you by telling what is the origin of this number theory and what are the applications and what are the prerequisites. And once again, I want to give some stress on cryptography. You know what is cryptography? That is originated from a Greek word whose meaning is secret writing. And what is encryption? The process of converting a plain text into cipher text, that is known to be encryption. So further, we may have to know about decryption, the process of converting a cipher text into original text, that is known as decryption. You know what is plain text? Whatever the message we are having, that is known to be a original message. And what is cipher text? The message after conversion, that is known to be encrypted message, that is also called a cipher text. So already I mentioned what are the mathematical prerequisites in order to get a mastery over cryptography. What we need? To mention a few, we may have to know Euclidean algorithm and its applications, modulo operator, that will be related to congruence theory and their applications. So which involves multiplicative inverse specially, and then Euler's totient function, as I mentioned earlier, Fermat theorem, and then a little bit of Chinese remainder theorem. So to start with, we want to get some fundamentals. You know, two integers, a and b, where a is non-zero, then we say that a divides b if there is a possibility of finding another integer c in such a manner that b is equal to ac. You will be in a position to express b as a product of a and c. There is a symbolic representation. Whenever a is dividing b, we can write a divides b. That can be seen in slide. Similarly, when a does not divide b, that is also symbol where a is not dividing b. A small example, I can give 4 divides 32. That is obvious. Why? Because 32 is a multiple of 4. Similarly, 8 does not divide 42. In other words, you cannot express 42 as a multiple of 8. You can have some propositions or lemmas or results. Suppose if a divides b and a divides c, then he also divides the sum of the denominators, namely b plus c. As an example, whenever 3 is dividing 6, 3 is dividing 9, so as 3 divides their sum, namely 6 plus 9, that is resulting as 15. And one more, if a divides b, then a also divides the multiples of b for all integers c. For example, whenever 5 is dividing 10, 5 also divides its multiple. Say 2 into 10, that is 20, 3 into 10, 30. That is 5 divides 20, 5 divides 30, and so on and so forth. And one more aspect, if a divides b, b divides c, then a is dividing c. This is known to be a transitive property. If a divides b, b divides c, a divides c. But you can observe the commutative property does not hold in number theory. A divides b does not mean that b divides a. Why? Because we are only engaging integers, as we are not touching rationals and real numbers. A small example I have posed, 4 divides 8, 8 divides 24 means 4 also divides 24. That is a divides b, b divides c means a divides c. You know very better what is prime number. A number which is divisible by 1 and itself is known to be a prime. Now we are looking at one important theorem that is known to be the fundamental theorem of arithmetic. We know every positive integer n greater than 1 that can be expressed uniquely as a product of primes irrespective of their order. This is known to be fundamental theorem of arithmetic, which plays a vital role in number theory. A small illustration I want to give, 15. 15, even though it is not prime by its original nature, it can be expressed as product of 2 primes. Similarly, 48. By the nature of 48, It may be an even number, but still it can be expressed as product of primes or at least product of prime powers. You know, 48 is 2 into 2 into 2 into 2 into 3, that is 2 power 4 into 3. This representation is known as canonical form, that is representing in terms of prime powers. Similarly, 17 by its nature, that is only a prime number. You need not express as product of anything. 100, even though it is not prime, it can be expressed as a product of prime powers, namely 2 square into 5 square. That is 4 into 25 is resulting as 100. Likewise, so many examples can be taken over to represent fundamental theorem of arithmetic. So they are only self-explanatory. So later on, we are now coming across one more important aspect that is known to be GCD, greatest common divisor between two integers a and b. When do you say that D has GCD of a and b? D has to divide a and D has to divide b. You pick up the common divisors of a and b together, and out of those common divisors, you have to extract the highest or greatest. That is known to be the GCD between a and b. Usually it is denoted by GCD open interval a and b. A small illustration, if you are asked to determine the GCD of 48 and 72, then pick up the divisors of 48 and then divisors of 72. Out of those divisors, pick up common divisors. They are found to be 1, 2, 3, 4, 6, 8, 12, 16, and 24. But we are very much interested to see the greatest, the highest one is 24. Therefore, the GCD between 48 and 72 can be taken as 24. Similarly, I want to give one more example to find the GCD between 19 and 72. As you can observe that 19 and 72, they do not have any common divisors, only except one. One is the only one common divisor. So GCD between 19 and 72 can be found as 1. In such a case, the two numbers are said to be relatively prime, as they are having their GCD as only 1. So not only this, you can determine GCD of given two numbers by using the prime factorization. So this method goes like this. Suppose two numbers are given, namely a and b, express them as a product of prime powers. Say a is equal to p1 power a1 into p2 power a2, so on pn power an. Similarly, b is equal to p1 power b1, p2 power b2, so on pn power bn. Then how to determine GCD between them? As p1 power, you have to pick up minimum of a1 b1. You have to compare the powers and then take minimum. Into p2 power, again compare powers, minimum of a2 b2, so on pn power minimum of an bn. A small illustration is given. For example, I want to determine GCD between first number 60 and second number 54 using canonical representation, that is also known to be prime powers. I want to express 60 as the product of prime powers, namely 2 square 3 power 1 into 5 power 1. Similarly, 54 can be expressed as 2 power 1 into 3 power 3. There is nothing is there. I can take 1. That 1 can be taken as 5 power 0. Why? Because we want to compare powers. Then to determine GCD between a and b, let us take the principle that is given in the above. So 2 power. So what is given? P1 power minimum of a1 b1. So I have to take 2 power minimum of prime powers 2 and 1 is 1. Next, second. What is second p2? Second prime 3. Compare powers. Minimum of 1 and 3 is 1. Similarly, last prime is 5. What are the powers? 1 and 0. What is the minimum? That is 0. So I can write this completely as 2 power 1, 3 power 1 into 5 power 0. That is resulting as 6. So and hence you can say that GCD between 60 and 54 as 6. So already I told, when do you say that two numbers are relatively prime? If their GCD is 1. A small illustration you can check. Are 15 and 28 relatively prime? Yes. They do not have any common divisors. That's why we can say them as relatively prime. Similarly, are 55 and 28, are they relatively prime? Let us see. Yes. Why? Because they also are not having any common divisors. GCD between them is 1, and hence they are also relatively prime. And one more question, are 35 and 28 relatively prime? Let us investigate. No. Apart from 1, they are having one more common divisor for both 35 and 28, namely 7, whose GCD is not becoming 1, and hence they are not relatively prime to each other. And not only between two integers, we can check the relatively primeness more than two integers. Say, what does that tell? Example, I will give are 15, 17 and 27. Are they pairwise relatively prime? According to theory, if GCD of AI comma AJ is 1, whenever I and J are lying between 1 and n, then the given numbers, that is more than 2, they are said to be relatively prime. So just I am checking whether 15, 17 and 27 are relatively prime or not. I want to check GCD between each prime, namely GCD between 15 and 17, and then 15 and 27, and 15 and 27. But we are finding that GCD between 15 and 27, it is found to be 3. Actually, we should get GCD between any two pairs as 1, but we are getting the GCD between 15 and 27 is 3. Why? Because 3 is a common divisor for both 15 as well as 27, and hence they are not relatively prime. And one more, are 15, 17 and 28, are they pairwise relatively prime? Let us check between two pairs, any two pairs, namely the GCD between first one 15, 17, as they do not have any common divisors, 1. Similarly, GCD between second pair 17 and 28, that is also found to be 1. And similarly, between 15 and 28, as they do not have any common divisor, their GCD is also 1, and hence all the pairs are resulting their GCD as 1, and hence they can be termed as pairwise relatively prime. So with this, we can step into another aspect of number theory, that is known to be division algorithm. All of us, we might have studied about division algorithm in our lower classes by knowingly or unknowingly. That is a relation between the dividend, divisor, quotient and remainder. You might have seen in your lower classes the relation. What is that relation? Dividend is equal to divisor into quotient plus remainder. That we are representing in mathematical way. That is, if A is an integer and D is a positive integer, or with 0 less than or is equal to r less than d in such a manner that A is equal to dq plus r, that is known to be division algorithm, where there is a nomenclature for each and every term. D is termed as divisor, A is called to be dividend, Q is called to be quotient, and R is remainder. And we must know that R is greater than or is equal to 0. It is whenever it is 0, division algorithm does not exist actually. It will become complete divisor. So R is always positive. At the most, it may be 0. For example, I want to divide 17 with 5. How can you represent in division algorithm? That is 5 into 3 plus 2. 17, you know, dividend, 5 is divisor. Divisor means which is dividing. 17 means which is getting divided. That is known as dividend. And 3 is called quotient. And 2, what is remaining? That is known to be remainder. And as we are seeing that remainder is always greater than 0, or at the most it may be 0. And one more, we can jump into, with the knowledge of this division algorithm, we can step into the Euclidean algorithm that plays a vital role in number theory as well as cryptography. The continuous appliance of division algorithm is known to be Euclidean algorithm. So it goes like this. You have to go on applying division algorithm, go on applying till you get a 0 remainder. So it goes like this. Say A is equal to Q1B plus R1. Similarly, B is equal to Q2 R1 plus R2. Similarly, R1 is equal to Q3 R2 plus R3. So on and so forth. You will get a stage where Rn minus 1 is equal to Qn plus 1 into Rn plus 0. Here remainder is becoming 0. But you just look at a previous step. You are getting a non-zero remainder Rn. That non-zero remainder Rn is said to be GCD between A and B. So this is the continuous appliance of division algorithm that is known to be Euclidean algorithm. I want to give a small illustration. For example, you are asked to find GCD between 328 and 296. Unlike in previous problem, you can tell orally or within no time, but it is to be studied and it is to be calculated. So always you divide a big number with small number, then you can represent 320 is 296 into 1 plus what is remaining 24. That is known to be remainder. The first quotient is Q0 and the first remainder is R0. Now, here we did not get remainder as 0. We are getting as 24. So the process should be continued. So if it is over within single step, that is known to be division algorithm, but it is to be continued. So this process is known to be Euclidean algorithm, that is applying again and again. So again, I am writing the second step. First step is seen, and again second step. 296 is 24 into 12 plus 8. The roles are changed. The divisor is becoming dividend and the remainder is becoming divisor. 296 can be written as 24 into 12 plus the remainder is 9. So can we stop? No. As you are not getting a remainder 0, but still change their roles and apply division algorithm continuously. This is known to be Euclidean algorithm. So once again, I wrote previous steps also. So 2 steps are already known. Again, this divisor 24 is becoming dividend and the remainder 8 is becoming divisor. I can express 24 as 8 into 3 plus 0. Now we are getting 0 remainder. As I told, you need to go a step before that. That 8 is known to be a non-zero remainder, that is known to be GCD between two numbers, the given numbers 320 and 296. This process is known to be Euclidean algorithm. And one more illustration you can see a GCD between 346 and 592. In a quick manner it can be found, it can be just seen, and we are getting so many number of steps, namely 592 is 346 into 1 plus 246. Again, change their roles. And 346, this divisor is becoming dividend, and the last remainder is becoming divisor. And that can be expressed as 346 is 246 into 1 plus 100. So on and so forth, till you get the last step, 6 is equal to 2 into 3 plus 0, where you are getting 0 remainder. Once again, you look at the last non-zero remainder in the previous step, that is found to be 2, and hence we can conclude that GCD between these two numbers as 2. And one more thing, you can also express this GCD as a linear combination of the given two numbers in terms of another two integers. Say GCD between A and B is SA plus TB, where S and T are any integers. Any integers means they may include positive or negative. Here A and B are positive integers, S and T may be any integers. This is known to be Budget's theorem. For example, after finding GCD between 6 and 14, you can express this GCD between 6 and 14 as in terms of linear combination in the form of SA plus TB. For any integers S and T, you can express this GCD as minus 2 into 6 plus 1 into 14. Here in place of S, we are getting minus 2, and in place of T, we are getting 1. So this is known as Budget's theorem, that is expressing GCD as a linear combination of given two integers A and B. In fact, you know, the GCD between 6 and 14 is what I did not tell you. You might have noticed. Here, according to RHS, 14 minus 12 is 2. So that 2 can be expressed as a linear combination of minus 2 into 6 plus 1 into 14 in terms of Budget's identity. So one more illustration, this is given. Finding GCD as a linear combination, you can just see. Finding GCD between 252 and 198, that is resulted as 18. just I am giving directly. So after making certain steps, that 18 can be expressed as a linear combination of, see the last step, 4 into 252 minus 5 into 198. I told already S and T may be any integers. S is 4, here T is minus 5. They are expressed as a linear combination of given two integers. The GCD between two numbers, namely 252 and 198, which is resulted at 18, that is expressed as linear combination of 252 and 198 by taking the values of S as 4 and T as minus 5. So this is a first slide, set of slides. Just I want to have one more set of slides. Now, I am more interested to see various types of numbers in number theory. I am very fascinated to know the details of some of the numbers. So they are known to be various numbers. Today I would like to express, namely perfect number, abundant number, deficient number, amicable number, Fibonacci number, and Lucas numbers. So to start with, let us take what is a perfect number. You know, a number is said to be perfect if it is equal to sum of its proper divisors. You have to exclude itself. The first example I am posing, 6. What are divisors of 6? We can get the divisors of 6 are 1, 2, 3. You have to exclude 6 itself. So sum of the divisors is becoming 1 plus 2 plus 3 is 6. You have to exclude 6 itself. So after 6, there is some gap. You cannot directly jump into 7 or 8. Now we may have to see only 28. Why? Because it is undergoing some principle. What is the principle? A number is said to be perfect if it is equal to sum of its proper divisors. 28 is one more perfect number. What are divisors of 28? 1, 2, 4, 7 and 14. You have to exclude 28 and sum up. What is sum? 1 plus 2 plus 4 plus 7 plus 14. That is resulted as 28. That is only the given number. So such numbers are known to be perfect numbers. And these are invented by Greek mathematicians. And so far, we may observe only the perfect numbers. They are only measured. They are only seen in even nature. No perfect number is found to be odd nature. Only we are seeing in terms of even nature. And after this,
can you make it full screen, sir, please?
And after this, we are coming across one more number that is known as deficient number. When do you say that a number is deficient? A number is said to be deficient if the sum of its proper divisors is less than the number itself. For example, out of several numbers, I am picking, say, 14. What are divisors of 14? Proper divisors of 14. Proper divisors of 14 are 1, 2, 7. I am not including 14. You sum up 1 plus 2, 3, 3 plus 7, 10. So what is there in the principle? A number is said to be deficient if the sum of its proper divisors is less than the given number. We got sum of the proper divisors of 14 is 1 plus 2 plus 7. That is only 10, which is less than 14. Hence, such a number is termed to be a deficient number. So contradicting to this, we are coming across abundant number. Abundant means something is flowing more than required. Now we can give its definition. A number is said to be abundant if the sum of its proper divisors is greater than the number itself. You can give one more example, 24. What are divisors of 24? 1, 2, 4, 6, 8, 12. I am excluding 24. If you sum up all these numbers, they will be greater than 24 itself. Hence, the given number 24 is said to be abundant. Small illustrations I posed. Here 12 proper divisors of 12, they are found to be, their sum is found to be 16. That is greater than original number, hence it is abundant. Similarly, 18 also one abundant. Just you observe, 12 is abundant, 18 is abundant, 15 I told deficient. And one more illustration, perfect. What is perfect number? I told a number is equal to sum of its proper divisors. That is perfect. And see, these are the ancient Greek mathematicians, Pythagoras, Euclid, Archimedes, and Eratosthenes. They shared their contribution very much for the development of number theory. Now I am giving the list of perfect numbers. Say P1 is 6, P2 is 28, having 2 digits. You observe, P3 is having 3 digits, namely 496. And P4 is 8128. Then you may imagine that P5 may be having 5 digits. That prediction will become wrong. P5 is having 8 digits. There is a huge jump between one perfect number to another perfect number. That is the beauty of number theory. And just I posed some of the illustrations. P1, P2, P3, P4. After this, you know, P5 is having 8 digits. P6 is having 10 digits. P7 is having 12 digits. P8 is having 19 digits. Then, you know, there is a huge jump. P9 is having 37 digits. So it has to obey the principle. What is the principle? A number is said to be perfect if it is equal to sum of its proper divisors. Similarly, P10 is having 54 digits. P4 is a huge number. Similarly, P11 is having 65 digits. And so on and so forth. P12 is having 77 digits. And you know, P13, you know how much big number is this? It is having 314 digits. A lot of research is going on to investigate about what is the next perfect number, what is next perfect number using supercomputers nowadays. And I am seeing at one more set of numbers. They are known to be amicable numbers. 2 numbers are said to be amicable if the sum of proper divisors of one will be equal to the other. For example, I am saying that 220 and 284 are amicable. They are having friendly nature. Why? The proper factors are divisors of 220. You have to exclude 220. Then you are getting 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110, whose sum is becoming 284. Similarly, see, they are, you know, mutual friends. Friendship means giving and taking. When 220 is friend of 284, 284 is also friend of 220. Now you find the proper divisors of 284 apart from itself. That is 1, 2, 4, 71 and 142, and whose sum is becoming again 220. See, from the nature of amicable, we can see that they are not giving importance to themselves. They are only giving importance to their fellow beings. That is, we can learn from amicable numbers. See, you know, 220 is not included. It is not bothering about herself. Similarly, 284 is not bothering about herself. It is only taking care of its vicinity numbers, excluding itself. Similarly, 284 is also not bothering about herself. So it is only taking care of the numbers in and around whose divisors, whose sum of divisors is becoming 142. So there is a message from amicable numbers. One should not look on himself or herself. They need to help others. That's what amicability develops. And even these amicable numbers are known by Greek mathematicians or Pythagoreans. Now I am coming across one more set of numbers that is known to be Fibonacci numbers. So actually it was invented by Leonardo da Vinci. He was a great scholar and then mathematician, painter, multi-personality. See, a small mathematical modeling is there in terms of rabbit for the originating of Fibonacci series. Just I am depicting. For example, two rabbits are there. Suppose a newly born pair of rabbits. One is male rabbit, another is a female rabbit. They are put in a field, and you assume this mathematical modeling, rabbits are able to mate at the age of 1 month, so that at the end of its second month, a female can produce another pair of rabbits. Remember, at the end of second month. Suppose that the rabbits never die. This is our constraint. This is our assumption. Suppose that the rabbits never die and that the female always produces one new pair, that is both one male as well as one female every month. That is from the second month onwards. Then how many pairs will be there after 1 year? That is our question. So in order to give response to this question, we need to depend on Fibonacci series. So let us discuss this problem or this mathematical modeling. At the end of 1 month, there is only one pair. So this is only one pair, as we discussed. Let us see what is happening. And at the end of second month, the female produces a new pair. See, in first pair, one is having male, one is having female. That female is giving birth to again one pair. One is having male, one is having female. So in total, at the end of 2 months, 2 pairs are generated. Apart from one more is originated. So in total, 2 pairs came into picture. So and then what is happening after next month? So again, it is illustrated from the beginning. So let us
Sir,
see.
full screen, sir, please.
Madam, this is not same. This example.
Okay. Okay, fine.
Okay. So at the end of second month, 2 pairs, as we have discussed. At the end of third month, what will happen? At the end of third month, the original female produces a second pair, making 3 pairs in total field. So what is happening? At the end of second month, 2 pairs are there, but at the end of second month, the original pair is giving birth to one more pair. Each time it will produce 2 members. One is male, another is a female. So at the end of third month, what is happening? The original female is producing a second pair, resulting in total as 3 pairs. That is when after the end of third month. Let us see what will happen at the end of fourth month. So from the beginning, I am depicting. So at the end of first month, 1 pair. At the end of second month, 2 pairs, as we have discussed. At the end of third month, 3 pairs. What is happening at the end of fourth month? At the end of fourth month, the first pair produces yet another new pair. Why? Because it will be producing at the end of every second month. So the first pair produces yet another new pair, and the female born 2 months ago, and even the last one which was born 2 months ago also produces one more pair, in total resulting as 5 pairs. So you just go on observing how the pairs are arranged. 1, 2, 3, 5. So now this has led to the origination of Fibonacci series. Thus we get the following sequence of numbers like 1, 2, 3, 4, 5, 8, 13, 21, 34, 55, 89, 144. So this sequence is known to be a Fibonacci sequence. You observe how it is calculated. You add the last 2 digits to get the next. Here we observe 1 plus 1 is 2. Again 1 plus 2 is 3. 2 plus 3 is 5. So the third number is sum of the first 2 at the beginning. So this series is known to be a Fibonacci series or Fibonacci sequence. And at the end of 1 year, we imagine that the pair of rabbits in total, they will become 144. So likewise, Leonardo da Vinci, he was responsible for the origination of Fibonacci numbers. You will be getting a tremendous and interesting applications of these Fibonacci numbers. How to recognize whether a given number is Fibonacci or not? Just we may have to see a polynomial, say 5x square plus 4 or 5x square minus 4, it should become as a perfect square for a given positive integer x to become whether it is a Fibonacci or not. For example, I want to test whether 5 is a Fibonacci number or not. Then what I have to depend? I need to depend on either 5x square plus 4 or 5x square minus 4. So this is just I am substituting in second one, that is 5 into 5 square. 25 into 5, 125 minus 4, 121, that is a perfect square. Why? Because 11 square is 121. So therefore you can take 5 as a Fibonacci number. You remember it should satisfy only one principle, either 5x square plus 4 or 5x square minus 4. Then only the positive integer x is said to be a Fibonacci number. Now let us observe one more that is known to be a Pascal triangle. You might have seen it when you are at intermediate, Pascal triangle in terms of while finding in probability and some other places, binomial theorem. You just observe the extreme diagonal here, the numbers, whatever the numbers we are seeing, these are only the Fibonacci numbers, that is 1, 1, 2, 3, 5, 8, 13. So these numbers are seen to be Fibonacci numbers where we are representing a Pascal triangle. So one more application of this, we are coming across a small definition, that is application of Fibonacci numbers, that is known to be a golden ratio. Two quantities are said to be in golden ratio if the sum of these quantities and the larger one is the same as the ratio between the larger one and the smaller one. For example, I am taking two quantities, namely A and B. So what does this theory tells? A and B are positive numbers where A is greater than B. Then the fraction, what is that fraction? The fraction A plus B by A, that will be same as A by B. So once again I am quoting, this is known to be golden ratio if the ratio between the sum of those quantities and the larger one is the same as the ratio between the larger one and smaller one. That is A plus B by A is same as A by B. That is denoted by 5. And the golden ratio is an irrational number. That is after some calculations it came, and it is to be assumed as 1.6180. That is called a golden ratio number. And what are the applications of these Fibonacci numbers? Especially we are dealing with computer science. They are part of your engineering people. So how it is applied in computer science, especially in searching a sorted array. So trees and algorithms you might be seeing at your MFCS. So it will be more useful in terms of searching a sorted array. And similarly, shapes of several natural and human-made objects are seen to obey the golden ratio. Similarly, some spirals in the flower plants and some monuments, they are also obeying this golden ratio that is only resulted as Fibonacci series. Fibonacci series has found many uses in architecture as well as engineering and widely seen even in nature also. So you can see how it is applied. See, just I want to give the list of some more Fibonacci numbers: 55, 89, 144, 233 and 377. This is a continuation of the old Fibonacci numbers. Just I want to make ratio of a bigger by smaller one, bigger by smaller one. See, it is having a constant ratio, that is 89 by 55, 144 by 89, that is 1.618, 1.618 approximately. That is known to be golden ratio. See, nature also, even from our flowers, we can see the Fibonacci nature. A flower is having one petal, a flower is having 3 petals, and another flower is having 5 petals, and this another flower is having 8 petals. This flower is having 13 petals. So what is significance? 1, 3, 5, 8, 13. All these known to be Fibonacci numbers. That is the beauty of Fibonacci. And even our human parts, especially our eyes, nose, ears, and arm, it will obey the golden ratio. So Fibonacci numbers, they are widely used for nature's monuments as well as even human parts. That is the beauty of number theory. And some more examples. This is golden rectangle, and one more rose flower. This is a Parthenon which was located at Greek. Even you can see the egg shape, rose shape, ear shape. All these will obey the golden ratio. That is A plus B by A is equal to A by B. That is coming around as 1.64. So this is only on account of knowing the Fibonacci series. Now we are coming across one more set of series that is called Lucas numbers. Now I am defining Lucas numbers. This is similar to Fibonacci numbers. Each Lucas number is defined to be the sum of its two immediate previous terms. The first two Lucas numbers, they are represented by L0 is equal to 2 and L1 is equal to 2. Unlike in Fibonacci series, you may take F0 is equal to 0 and F1 is equal to 1. You may observe the Lucas numbers 2, 1, 3, 4, 7, 11, 18, 29. See what is the beauty of Lucas numbers? How does it go? This is defined as the sum of its first immediate terms. Sum of a number is resulting as this. A number is resulted as sum of its two immediate previous terms. You know, 3 is sum of 2 plus 1. 4 is sum of 1 plus 3. 7 is sum of its preceding two terms, 3 and 4. 11 is sum of its preceding two terms, 4 and 7. 18 is sum of its two preceding terms, namely 7 and 11. Likewise, we can discuss various types of numbers in number theory. So before starting the primal test, I have given the list of these numbers. Now I am sharing another set of slides. You can come across the testing of primality. That also very useful in cryptography. So many tests are there to test whether a given number is prime or not. Today I am discussing some of the known tests. That is, whosoever are doing research in number theory, they will be knowing. That is Sivan-Ferrostany's square root method, Fermat primes, prime number theorem, etc. So you know what is prime number and composite number. So I am starting first method, that is known to be Sivan-Ferrostany's. So how does it start? Sivan-Ferrostany's, he was a Greek mathematician. Siva means, that is, in Telugu you may take it as Jaleda. So just we are searching for prime numbers between any two. Suppose I want to list out all the primes between 1 to 100. Then what is the algorithm? How does it go? One is neither prime nor composite. Just you strike off. Then start with a first prime, exclude the first prime, and go on striking the multiples of 2. Do not touch the first prime. Go on striking. Then how does it look like? All the multiples of 2 are, cancelled till the end, 100. Right from 4 onwards. You should not touch 2. Why? Because we are in search of prime numbers. 2. First prime is 2. Only cut down its multiples. So once this process is over, now start with another prime, that is 3, and see their multiples. What are the multiples of 3? You have to exclude 3. Don't cut it down. See, cut down starting with 6, 9, 12. Already 2 is cut down. Don't bother. But whosoever are remaining, you go on cutting till the end number is 99. It is given in another color. So likewise, again start with another prime 5. Exclude 5 and cut down its multiples. See, likewise, this process will be continued till the end. That is 100 is already cut down. So you have to cut down 95. Again, you take another prime, begin with 7 and cut down its multiples, exclude 7. Likewise, you will be continuing this process our aim is to find the list of prime numbers between 1 to 100. So likewise, 7, cut down its multiples, exclude 7. See here 49 is visible with another color, 77 is visible with another color, 91 and so on. Again start with another prime, 11, cut down its multiple, exclude 11 itself. And this process is continued. And what are the remaining numbers? And again you may...
Screen output, sir.
Is it visible?
No, sir. Screen share is...
Screen output only.
Now is it visible, sir?
No, sir.
Not visible. Just say. Adjust.
You didn't start screen sharing, sir. You were delivering talk.
Okay.
Sir, we are supposed to have a break at 10:15. Do you want to take a break or continue the session, sir?
No. Break is there. Sir, take the break.
Okay, now is it visible, sir?
Yes, sir, it's visible.
Srinivas, sir. Sir.
Sir, is it visible?
Yes, sir.
You have to take break.
I will take after 10 minutes, sir.
Okay, sir.
Sir, now is it visible?
Yes, sir.
Now,
You share the screen, sir. Assignment, some problems, 10 problems.
no. Just after completing this, I will share, sir.
Okay, sir.
Now, is it visible?
Yes, sir. Yes, sir.
Now, see this method, now I am testing the primality of given numbers by using different methods, say Siva-Ferrostani square root method, Fermat number and prime number theorem. So, you know, already I have discussed what is prime number. Now, the Siva-Ferrostani, this I discussed earlier. See, I want to know the list of primes between 1 to 100. I want to start with 2 and cut down its multiples. 1 is neither prime nor composite. So you ignore 1, take 2, cut down its multiples. You go on cutting its multiples. Similarly, start with another prime. Another prime, do not touch it, but cut down its multiples. How does it look like? So 3 is taken and we are cutting its multiples. This process will be continued till you get the prime number. Sorry, that is the last number 99. Similarly, start with a new prime 5. Don't cut down itself, only cut its multiples. Then how does it look like? So 25, 35, 55, 65, 95. And again start with a new prime. 49, it is cutting 49 and 77. You exclude 7. Similarly, cut down the multiples of 11, exclude itself. Likewise, we will be arranging, cutting the multiples of 11, then take the multiples of 13, exclude itself. Then whatever the remaining numbers are there in the screen, between 1 to 100, which are remained, they can be termed as prime numbers. This is known to be the method of Siva-Ferrostani. So what are the prime numbers? They are running from 2, 3, 5, 7, 11 up to 97. So this is known to be Siva-Ferrostani. So now I want to give one more method, method of primality testing by using square root method. How can you predict the given number is prime or not? This can be known that if the number is divisible by all the primes less than root n, then we can say that the given number is composite. Otherwise, it is said to be a prime number. So what is the principle? If the number is divisible by all primes less than root n, if it is not so, then the number is prime. Otherwise, it is a composite. For example, I am testing the primality of 97. See, if somebody is asking whether 97 is prime or not, you may tell or may not tell, but you may adopt a procedure, that is the method of square roots. What is the square root of 97? That is 9 point something, but we are taking integer part. The greatest integer not greater than that is only 9. The principle goes like this. Pick up all the primes less than 9. What are the primes which are less than 9? They are 2, 3, 5 and 7. See, these prime numbers, they are dividing 97 or not. But fortunately, none of these numbers are dividing 97. Hence, this 97 can be termed as a prime number. Similarly, we want to check whether 301 is a prime or not. So again, take its the square root. Floor function means you have to take the greatest integer not greater than that of that square root. So root of 301 is found to be 17 point something. Then we need to take the integer part of 17. Then what are the primes which are less than 17? They are only 2, 3, 5, 7, 11 and 13. But out of these numbers, let us check. Some are dividing and some are not dividing. The numbers 2, 3 and 5, they are not dividing 301. But 7 is dividing 301. According to our principle, none of the numbers should divide that number. But here 7 is dividing 301. Hence, you can say that 301 is not a prime number. Now, there are so many aspects to generate primes. We can see number of polynomial tests. One of such polynomial test is testing of polynomial of the form n square plus 1, where n is a positive integer. So many investigations are going on to test whether a given number is prime or not. You have seen first one is Siva-Ferrostani, second one is square root method, third one is n square plus 1, where n is a positive integer. For example, I want to give n as 1. Then what is 1 square plus 1? It is resulting as 2. For example, I want to take n is equal to 2. What is 2 square plus 1? 4 plus 1 is 5. That is also prime. But you know, it will not stand as universal principle. At some stage, it is failing. For example, n is equal to 3. Then what is 3 square plus 1? 9 square plus 1 is 10, which is not prime. So some are becoming prime, some are not becoming prime. Hence, lot of research is going on to investigate the nature of primes by using several polynomial functions. As such, we can give one more method that is known to be one more method in terms of polynomial. F of n is equal to n square minus n plus 41. It stands as prime for all integers right from 1 to 40. So unfortunately, f of 41 is becoming 41 square. That is not a prime number. So more generally, we can say that there is no polynomial in this nature with integer coefficients in such a manner that f of n is prime for all positive integers n. Somewhere else it is failing. Hence, a lot of research is going on to investigate the nature of primes, where they are coming from, how to see the nature of primes. That is the beauty of primality testing. And one more theory, this is known as Goldbach conjecture. To know whether a given number is prime or not, what does this Goldbach conjecture say? Every even integer greater than 2, it can be expressed as a sum of 2 primes. So according to Goldbach conjecture, what is saying? Every even integer greater than 2, it can be expressed as sum of 2 primes. For example, I am taking one even integer, say 6. 6, can you express as sum of 2 primes? Yes. 6 can be expressed as 3 plus 3. The 2 primes may be equal, don't bother. But that given even integer, it should be expressed as sum of 2 primes. I want to take one more example, say 10. That is an even integer. According to Goldbach conjecture, that 10 should be expressed as sum of 2 primes. Is it possible to express 10 as sum of 2 primes? Yes. I may express 10 as 2 ways. More than one way is also permissible. First one is 5 plus y. Second one is 7 plus 3. So far as there is nothing formula like that to predict about the nature of prime numbers. All these are termed as open problems in number theory. And you can see one more conjecture. Before that, we will be observing that there are infinitely many primes. We can come across that there are infinitely many primes in our number theory. So not only that, you can also see the twin prime conjecture. What are twin primes? They appear with a difference of 2. What are the best examples of twin primes? 3, 5, 5, 7, 11, 13, etc. In the current world's record, what is the biggest twin prime that is having, 1 lakh, around 1 lakh decimal digits? That is given a big number that was found in mid 2011. So it is consisting of huge digits, and that is known to be the world's largest twin prime. It is represented with plus or minus form. Again, lot of research is going on to trace about what is the biggest twin prime further. So not only this, we can also see Mersenne prime. So before starting this Mersenne prime and prime number theory, I want to give a small break. Let us take a break of 5 minutes.
Thank you, sir. I request all the participants to be tuned so that we can meet again after 5 minutes.
Srinivas sir.
Sir.
Went
Hello?
on well.
Hello?
Srinivas sir, నేను రాజారెడ్డి సార్.
సార్ చెప్పండి.
సార్ రాజారెడ్డి సార్ తర్వాత మాట్లాడండి.
ఓకే ఓకే ఫైన్.
సార్ చెప్పండి.
It went on well, sir.
Sir?
It went on well.
Okay. You want to convey some message?
No. So good. Keep it continue.
Okay. So, shall we take break for 5 minutes?
Yes, sir.
Okay.
Sir, you can mute your video.
లేదు మేడం, స్క్రీన్ షేర్ చేసిన.
Okay. Sir, video on undi. He has an option, I think. It's up to you, sir. Okay, thank you.
యూట్యూబ్ లో చూడండి ఏమిస్తుంది. అందరికి అది రాదు. అన్నా లేదు, ఇప్పుడు బ్రేక్ స్లైడ్ పెట్టినా, అందుకే మీరు మాట్లాడొద్దని చెప్పినాను. ఫోన్ చేసి అప్పుడు మాట్లాడదురు. ఓటర్ థ్యాంక్స్.
ఫోన్ లైవ్ లో వినబడుతుంది, మ్యూట్
బ్రేక్ స్లైడ్ పెట్టినాను.
నీ ఫోన్ నీది మ్యూట్ పెట్టి మాట్లాడు. ఫోన్ మాట్లాడేది వినబడుతుంది.
లైవ్ ఆఫ్ చేయి. లైవ్ వస్తుంది, ఆఫ్ చేయాలి. స్ట్రీమ్ ఆఫ్ చేయి. లైవ్ అని వస్తుంది. లైవ్ ఆఫ్ చేయడానికి రాదా? ఉండండి, పట్టింది. మనం జనరల్ గా ఫోన్ కాల్ చేసుకుందాం కావాల్సి.
Shall we resume the session?
Sir has come. Sir came into the picture.
Hello?
Shall we
Yes,
resume
sir.
the sessions?
Yes, madam. Yes, madam. You
Okay,
can.
sir. Yes.
వినపడుతుందా అండి?
Yes, sir. Yes, sir.
ఓకే, మీరు PPTs whenever they are not visible, you remind me, madam.
Sure, sir. Thank you. I'll do that.
Okay.
Sir, can I make a small announcement? Few people are posting the questions in the chat box of YouTube. I request
They will
all the
be-
participants.
They will be catered later on.
Yes, sure.
In doubts clarification.
Yeah, we have a doubts clarification session right from 11:50 to 12:20.
No, madam. That is after. It may take another 1 hour minimum. We will see.
Yes, sir. Okay. After this
After session,
lecture
we
is
will-
done. Yes, sure. Please post your questions in the Facebook chat box. Thank you. Sir, you have muted your video. Switch on the. Yes, sir.
Yes.
Is it visible, madam?
Yes, sir. Yes, sir.
That is Mersini primes.
Yes, sir. It's visible. Mersini primes definition.
Shall we wait for some time or shall I continue?
We will proceed, sir. Yes.
Okay. See, in the last session, I have explained about what is the twin prime conjecture theory. Now I am starting what is the Mersini primes. A number is of the form 2 power p minus 1, where p is called, that is known as a Mersini prime. Here p should be a prime. So we want to look at numbers of the form 2 power p minus 1. So on putting p is equal to 2, you are getting 2 square minus 1, that is 3. On putting p is equal to 3, you are getting 2 cube minus 1, that is 7. And on putting p is equal to 5, you are getting 31, and so on and so forth. But you know, it is similar to the previous case. At some stage, the tracing of prime numbers is failing. Unfortunately, on keeping p is equal to 11, 2 power 11 minus 1, that is coming as around 2047. But that is not found to be a prime. Why? Because 2047 can be expressed as 23 into 89. So hence, in search of primes is not ending. So many systems are evolved to trace out the nature of primes. As such, the great internet Mersini prime search GIMPS is a distributed computing project to search for new Mersini primes. So they can be evolved using supercomputers. So as of now, only 47 Mersini primes have been traced out. They will be having some 13 million decimal digits, which is given in the slide, having 2 power 43 lakhs 11,206.09 minus 1, which is having nearly 13 million decimal digits. So lot of research is going on to investigate about next Mersini primes. So Mersini, he was a French mathematician who was responsible for the origin of a prime of the form 2 power p minus 1. Just look at this slide again. So what we found was previously up to 2 power 7 minus 1, it is obeying the prime nature. Whereas on putting p is equal to 11, 2 power 11 minus 1 is not found to be prime, that is 2047. Now I want to compare a Mersini prime with a perfect number. Just you can see, if 2 power n minus 1 is a Mersini prime, then 2 power n minus 1 into 2 power n minus 1 is a perfect number. You look at this. For example, n is equal to, you take 2. 2 square minus 1 into 2 power 2 minus 1. That is 2 square minus 1 is 4 minus 1 is resulted as 3 into 2. 3 into 2 is 6. So that is the outcome of first perfect number. There is a link between Mersenne prime and perfect number. On multiplying 2 power n minus 1 with 2 power n minus 1, you can generate perfect number. Similarly, on putting p is equal to, say n is equal to 3, you calculate 2 power 3 minus 1 into 2 power 3 minus 1. So put n is equal to 3 next time. 2 power 3 minus 1, that is 8, minus 1 is 7, into 2 power n minus 1. On keeping n is equal to 3, 2 power n minus 1 is 2 square. So 7 into 4 is resulting as 28. So that is becoming a second perfect number. See, likewise, you can see the relation between Mersenne prime and perfect numbers. So there is another sort of prime theory. Look at this slide. Who is he? He is only a Fermat. So his contribution is a lot for number theory. Just look at another aspect of his theory. In the generation of primes, he has given numbers of the form. He has given numbers of the form 2 power n plus 1. These are known to be Fermat primes. A numbers of the form f is equal to 2 power n plus 1. They are known to be Fermat primes. You can substitute some values. See, for example, on putting n is equal to 0, we are getting Fermat first prime. Say that is 3. On putting n is equal to 1, you are getting f1. Second prime is 5. And on putting n is equal to 2, you substitute in 2 power n plus 1. That is resulting as 17. Similarly, keep n is equal to 3 in 2 power n plus 1. That is coming as 256 plus 1. That is only 257. See, unfortunately, we are getting only the set of primes. The next is not becoming prime. So that is the beauty of number theory. At somewhere else it is failing. Hence, lot of research is going in search of next prime number. So these are only F0, F1, F2, F3 and F4 is also found to be prime. But at F5, it is failing. That is not found to be a prime. Only according to Fermat's number theory, the first 5 are only originated as prime numbers according to this 2 power n plus 1 principle. So not only that, there was one more theory that is known to be a prime number theory. So we are in search of prime numbers. This theory goes like this. This is called a prime number theorem. The ratio of the number of primes not exceeding x and x by ln of x. ln means the natural logarithm of x. You have to take to the base of e. So what we are seeing is the ratio of number of primes not exceeding x and x by logarithm of x. It will be approaching to 1 for large values of x. So in other words, this theorem tells that the number of primes not exceeding x, they can be approximated by x by its logarithm of x. We need to take the natural logarithm to the base e. For example, I am taking x as 1000. See, according to this prime number theory, the number of primes up to 1000 are 168. But without even calculating, they can be approximated by taking the formula x by log x. Log x is only to the base of e. So what we need to calculate is 1000 by log 1000, but it is coming as 145. To get a better approximation, the denominator is converted from log x to log x minus 1. Just like in sampling theory, you might have seen probability statistics. what is the best approximation? Sample standard deviation, square root of sigma x minus x bar whole square by n minus 1. Instead of taking n, there you are taking n minus 1 to get better approximation. Similarly, if you take x by log x, number of primes are found to be 145 as against 168. But if you take x by log x minus 1, this is somewhat closer to the actual prime numbers up to 1000. That is 168 and 169 somewhat nearer. Similarly, I want to find number of primes up to 10,000. So actual numbers are 1229. If you calculate using x by log x, they are found to be 1086. But to get more accuracy, we are changing the denominator, that is x by log x minus 1. By taking that formula, you are getting 1218. That is somewhat near to 1229. So this theory says that the number of primes up to x, that is equivalent to x by log x. In turn, in practical, that should be taken as equivalent to x by log x minus 1. So all these come under testing of prime numbers. Now I want to take another set of slides. Starting with congruences. Yes. So this is a lecture on modular arithmetic and their applications. This set of slides they involve congruences and their properties, linear congruence and their solutions, and what are the general applications of these congruences. Actually, they will be used in generation of pseudo-random numbers and then finding the correct digit of ISBN number. Let us see first.
Can we move to full screen? Yes, sir.
See, for example, I am starting with say 3 integers, namely a, b, n, where n is positive. Then we say that a is congruent to b mod n if and only if n divides a minus b. So here there is terminology. N is said to be modulus, b is called remainder. See, a is congruent to b mod n. Remember, if and only if n divides a minus b. Here n is called modulus and b is called remainder. You can see some illustrations. 29 is congruent to 15 mod 7. Why? Why? Because the 7 is dividing, n is dividing a minus b. 7 is dividing the difference of 29 and 15. You can also tell in other way, 29 is leaving the remainder 15 when it is divided by 7. It is leaving the remainder 15. Similarly, you can say that 12 is congruent to 3 mod 9. Why? Because, you know, when 12 is congruent to 3 mod 9, how it is possible? 9 is dividing the difference between 12 and 3. Similarly, you can see some more examples. They are given on the slide. Now you can also coming across the addition and subtraction properties in modular arithmetic. For example, a mod n plus b mod n whole mod n, that will be termed as a plus b mod n. Similarly, I want to subtract now. A mod n minus b mod n whole mod n, that will be resulting as a minus b mod n. Similarly, multiplication also works. A mod n into b mod n whole mod n is equal to a into b mod n. The proofs can be easily seen in any one of the books, even in slides. Let us look at some examples. For example, I am giving 11 mod 8 is 3. Why? On dividing 11 with 8, it is leaving the remainder 3. Similarly, on dividing 15 with 8, it is leaving the remainder 7. It is of the form a mod n and B mod n. So I am applying the first principle. 11 mod 8 plus B mod n means 15 mod 8 whole mod 8. So what is left side? That is 11 mod 8 plus 15 mod 8 is 11 plus 15 mod 8. 11 plus 15 is 26 mod 8. So what is the remainder? When 26 is divided by 8, it is leaving the remainder 2. So this is general application of first addition principle. A mod n plus B mod n whole mod n, that will be calculated as A plus B mod n. Similarly, it may be true even for subtraction. A mod n minus B mod n whole mod n is A minus B mod n. You investigate on your own within no time. It is visible on the screen. Second example. That is only self-explanatory. Just have a look on the screen and satisfy yourself. Similarly, another half minute is given to investigate about product, that is A mod n into B mod n whole mod n, that will be resulting as A into B mod n by taking same numbers. In place of A 11, in place of N 8, in place of B 15. Find product of 11 mod 8 into 15 mod 8 whole mod 8. You know 11 mod 8 is 3, 15 mod 8 is 7, 3 7s are 21 on right side, and again it is divided by 8, it is resulted as 5. It should be is equal to the right side. What is the right side? A into B mod n, that is 11 into 15, 165. When divided by 8, it is resulted as 5. So likewise, you can verify the addition, subtraction, and multiplication. Our main concern is to see the division. Division plays an important role. You know, two integers, A by B, you may not get another integer. There is no guarantee. So instead of division, we multiply with its multiplicative inverse. So that plays a vital role in cryptography. So for that, we need to look at two definitions. That is ZM, set of integer modulo m. So it is running from 0, 1 to m minus 1. Then we can define two operations, namely addition modulo m and multiplication modulo m. So how you define addition modulo m between two integers A and B? A plus B mod m is the least positive integer obtained when A plus B is divided by m. This is known as addition modulo m. Similarly, A into B mod m, that is the least positive remainder obtained when A into B is divided by m. For example, I am picking two integers 7 and 9. So let us see what is addition modulo and multiplication modulo. 7 plus 9 modulo 11, that is 7 plus 9 is 16. 16 on dividing with 11, it is leaving the remainder 5. Similarly, let us look at multiplication. 7 into 9, that is 63. When it is divided by 11, it is resulting as 8. So for this, we need to see even what is additive inverse and multiplicative inverse. You might have seen it group theory. Group theory, you can see this is only Z10, that is running from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9 in row wise as well as column wise. For example, I want to see the additive inverse of a number, say 4. What is additive inverse of 4? That will be only 6. If you operate a number with its additive inverse, you should get additive identity. That is 4 plus 6 mod 10 is only 10 mod 10. That is, the remainder is 0. So hence 4 is the inverse of 6. So not only this, let us look at modular multiplication. So I want to look at modular multiplication. For example, same, I took the table. Suppose I want to find the multiplicative inverse of 3. Multiplicative inverse of 3. You know, each and every number present in the composition table, it need not have multiplicative inverse. The numbers which are only prime to 10, they only have multiplicative inverse. See, what are the numbers which are less than 10 and which are relatively prime to 10? They are only 1, 3, 7, 9. They will be having only multiplicative inverse. See, for example, see the composition table. I want to find the multiplicative inverse of 7. Where you are getting the matching number as 1, the row headed by 3 and column headed by, row headed by 7 and column headed by 3, they are coinciding at 1. Why? Because 7 into 3 is 21. 21 when on divided by 10, it is leaving the remainder 1. Hence, only some numbers are having multiplicative inverse which are relatively prime to mod m. So this is a small information about addition modulo and multiplication modulo. Now let us look at one more theory that is known as linear congruence. So I am more interested to see the linear congruence and its solution. A congruence is of the form X is congruent to B mod m. That is known to be a linear congruence. What is the description of terms here? M is a positive integer, A and B are any integers, and X is a variable. Such a representation is known as a linear congruence. And the solutions to the linear congruence are all the values of X which satisfy the given congruence. I want to solve the solution of given linear congruence by using the inverse modulo method. For this, I need to take a definition. An integer a bar is said to be an inverse modulo of a mod m if it satisfies the condition, say a bar a is congruent to 1 mod m. So already I have discussed, if you multiply a number with its multiplicative inverse, it is to be resulted as 1 on dividing with m. For example, you know the modulo table 7, 5 is an inverse of 3. Why? Because when you multiply 5 with 3, it is resulted as 15. On dividing with 7, it is again resulted as 1. Hence, you can say that 5 is an inverse of 3 modulo 7. But what is the condition? You can represent in the form of theorem. So what is that theorem? If a and m are relatively prime integers and m greater than 1, then only the inverse of a modulo m exists. In other words, the inverse of a modulo m exists whenever a and m are relatively prime. You know, when do you say that two integers are relatively prime? Whenever their GCD is 1. So let us see. What is the inverse of 3 modulo 7? Already I have seen. 5 is an inverse of 3 modulo 7. When does it exist? First of all, 3 modulo 7 exists provided GCD between 3 and 7 should be 1. And if you multiply this 3 with another number and on division with 7, it is to be resulted as only 1. So you can say that 5 is an inverse of 3. Why? Because on multiplying, you are getting 15 and on division with 7, it is resulted as 1. Similarly, I am asking, what is inverse of 4 modulo 9? So you can say that 7 is an inverse of 4 modulo 9. Why? On multiplying 7 with 4, you are getting 28. And again dividing this 28 with 9, it is resulted as 1. And under what condition? It will exist only whenever the GCD of A and M, namely GCD of 4 and 9 is 1. And you can make one note, one method of solving linear congruences make use of an inverse method if it exists. Although we do not divide both sides of the congruence, but only we multiply with its inverse to find the value of solution of the given linear congruence. For example, I want to find the solutions of or solution of linear congruence. Say 4x is congruent to 5 mod 9. So it is on the form ax is congruent to b mod m. So it will be having solution. Why? Because GCD of 4 and 9 is 1. And moreover, I want to make use of inverse method. Whenever 4x is congruent to 5 mod 9, I am multiplying both sides with, actually I want to divide with 4. Division of 4 is same as taking multiplicative inverse. of 4. That is, in turn, I can write x is congruent to 4 inverse mod 9. So I can write the first step as, in turn, x is congruent to 4 inverse mod 9 into the number present on RHS. It is kept as it is. What is inverse of 4 mod 9? I explained earlier also. Inverse of 4 mod 9 exists. Why? Because GCD of 4 and 9 is 1. Moreover, if you multiply 4 with some other number and dividing with 9, it is to be resulted as 1. So what is that number? So 4 is to be multiplied with 7. So 4 sevens, you can get 28. On dividing 28 with 9, it is leaving the remainder 1. Hence, you can say 7 is the only inverse of 4 mod 9. Now what is again on RHS? The 7 into 5 is remaining. 7 5 is 35 mod 9. So this 35 is bigger compared to 9. So again you need to find the remainder. So 35 by 9, it is leaving the remainder as 8. So hence what is solution? So solution to the congruence are integers x such that x is congruent to 8 mod 9. So this is the way to find the solution of linear congruence by making use of inverse modulo m. So not only that, you can also use the application of Euclidean algorithm to find inverse modulo m. For example, you are asked to find inverse of 101 modulo 4620. If it is 7 modulo m or 9 modulo, you would have taken some table. By taking all the numbers, multiplication is possible, but it is very difficult to multiply the numbers when a table having a modulo of 4620 is taken. So to overcome that problem, we are depending morely on application of Euclidean algorithm. It plays a vital role here. So the first step, for example, it is given to find the inverse of 101 modulo 4620. The thing is, you need to find the GCD between 101 and 4620. So let us recapitulate the methodology of Euclidean algorithm to find GCD between two given integers. As I explained earlier, you have to divide a bigger number with a smaller number. 4620 can be expressed as 45 times 101 plus the remainder is 75. And again, I told earlier, the roles will be changed. The divisor is becoming dividend and the remainder is becoming quotient. Again, in turn, you write 101 is 1 into 75 plus 26, so on and so forth, till you get a zero remainder. Say 2 is equal to 2 into 1 plus 0. So what is the last non-zero remainder? You observe carefully on the left side. The last non-zero remainder is 1. Hence, the GCD between the two given numbers, it can be taken as 1. So not only that, you are working backwards to find the inverse modulo, inverse of 101 modulo 4620. Let us work from back side. So how will you write? From the last but one step, 1 is equal to, I will write 3 minus 1 into 2. Again, 1 is equal to 3 minus 1 into C. What is the value of this 2? 2 can be seen from last but 2 step. That is 23 minus 7 into 3. So that is resulted as 3 minus 1 into 23 minus into minus plus. That is 7 into 3. That is resulted as minus 1 into 23 plus 8 into 3. Again, you write this is minus 1 into 23 plus. I want to express the 23 value. What is 23 value from last but fourth step? That is 75. 23 value. That is 75 minus 2 into 26. That is resulted as, on simplification, 26 into 26 minus 9 into 75. In turn, if you go on applying like this from backward, our aim is to express in the form of the S into T. I explained S is minus 35, T is 1601. These two integers in terms of Budget's identity as explained in the session 1. So finally you are getting 1 is equal to minus 35 into 4620 plus 1601 into 101. But our aim is to find the inverse of 101 modulo 4620, means you need to divide the last equation with 4620. On dividing the last equation with 4620, the right hand side part 1 is becoming 0. Why? Because the remainder is 0. On dividing 35 into 4620 with 4620, remainder is 0. So what is left out? So 1601 into 101. And hence you can say that 1601 is an additive is an inverse of 101 4620. This is only possible by using the methodology of Euclidean algorithm. So now I want to see some of the applications of congruences. So the first application as such, the generation of pseudo random numbers. So random numbers chosen, these are only chosen numbers. They are needed for many purposes, especially in simulations. Pseudo random numbers are not true random numbers, since they are generated by using certain algorithms, certain systematic methods. So one of such methodologies is by making use of linear congruential method to generate pseudo random numbers. This theory goes like this: by taking four integers are needed, namely modulus m, the multiplier a, the increment c, and the seed value, that is the initial value x0, where a lies between 2 and m, that is a may be equal to 2, and c lies between 0 and m, and c may be even 0, and x0 lies between 0 and m, and x0 sometimes it may be 0. Then by applying the method of linear congruential method, we are taking a formula xn plus 1 is, actually it should be written congruent to axn plus c plus axn plus c into mod m. So it is only linear type, where xn lies between 0 and m for all n. For certain choices of m, c, x0, the sequence xn becomes periodic. Again, it will be repeated again and again. That is, after a certain point, the sequence begins to repeat. The higher the period, the better will be the performance. So that's what we take the larger values of m usually to generate pseudo random numbers. Especially they play a vital role in simulations. For example, I want to generate a set of pseudo random numbers by taking a value of m as 9, multiplier a as c, increment c as 4, and initial value x0 as m. By taking the formula xn plus 1 is congruent, actually you can take 7xn plus 4 mod m with initial value x0 is 3. So you go on applying the values. Say put n is equal to here 0. What is the first value? x1. x1 is 7x0 plus 4 mod 9. Again, I am assuming x0 is 3. That is 7 into 3 plus 4 mod 9. That is actually 7 3 is a 21 plus 4. That is 25 mod 9. That is resulted as 7. Likewise, go on giving values. x2. How to obtain x2 value? On putting n is equal to 1, you are getting as at last 8. Similarly, by putting n is equal to 2, you are getting 6. Likewise, find x3, x4, x5, x6, x7, x8, x9. So all the numbers between 0 and 9 are generated. So again, if you find x10, the numbers will be repeated with some periodicity. The sequence will be generated like this: 3, 7, 8, 6, 1, 2, 0, 4, 5, 3, 7, 8, 6. Again, it will be repeated again and again. So it repeats after generating 9 terms. It wholly depends on the value of m. As you have taken m is equal to 9, the sequence will be repeated after 9 terms. This is only a theoretical aspect, but in general, in practical, while doing simulations, they will be taking a large value of m to generate a more number of pseudo random generals, where they play a crucial role in generation of pseudo random numbers. This is only one application. Similarly, I want to take one more application. As you are aware of ISBN number, some of you may be authors of some books. What is ISBN? It stands International Standard Book Number. ISBN means International Standard Book Number. You may see at the end of each and every book, it will be having a 10-digit number. So what is the description of these 10 digits? For example, I am giving a ISBN number for our, say, some textbook having 10 digits, namely 0-7167-5965-9. So what does this first digit represent? So this represents, this is a country where you are speaking English. That is only English speaking country. Most of the countries are only adopting English. Similarly, the next 4 digits, they represent publisher ID. You know, so many number of publishers are there in market. So they will be having their own publisher ID. Similarly, another 4 digits, they represent book ID. Next, this is more crucial, last digit, that is known as check digit. So by looking this check digit only, we can assert the given book is the original one or having fake ISBN number. Nowadays, we are seeing fake ISBN or fake journals are appeared in many sites where UGC has abolished. In the recent past, you have seen by cloning method, they are giving the fake journals. To overcome such kind of all these practices, we are using the application of modular properties. Let us see one example. For example, the ISBN 10-digit number, it goes by adopting an algorithm. So it looks like this. So what you have to do is multiply the first digit by 10, the second digit by 9, the third digit by 8, and so on until the last check digit, that is the 10th digit, you have to multiply with 1, and they should be congruent to 11. You know, if you take 0, 1, 2, 3, 4, that will be congruent to mod 5. Similarly, if you take 0, 1, 2, 3, 4, 5, it is congruent to mod 6. So if you are taking 10 numbers, it will be congruent to 11. So let us take a small example. A certain textbook is having ISBN number 1-2855-6352-C, where C is the last digit, that is known to be check digit. Let us determine what is the value of that number. So if you want to trace out what is the best possible value of C by using the modular arithmetic, first we multiply appropriately as per our algorithm. So what I told, multiply the first with 10 and second with 9, go on adding 8 with 8, 7 with 5, 6 with 5, so on and so forth. Last but one digit, 2 with 2, and last digit C with 1, you add up, and it should be congruent to 7. Congruent means it has to leave some remainder on dividing with 11. So it should be congruent to C. What is the best possible value of C on division with 11? So you can choose the nearest value of C. Only you can take, that is multiple of C. You can take, those numbers are 198, 209 and 220. All these numbers will be divided by 11. But the best possible number I can choose as, we add 218 plus C as 2, we will get a multiple of 11. So the best possible value of C is only 2. See, in that way, you can apply the congruences and modular arithmetic. So these are some aspects of applications of number theory. See, after this, I want to take one more set of slides having Fermat theorem and Euler theorem. See, I am taking now model exponentiation, Fermat theorem, Euler tangent function, and Euler's theorem. And a little bit of some applications numerically. See, before that, I want to see an application of modular arithmetic again. So I want to see a big number divided by certain number. Sometimes the students or researchers who are writing for set or net exam, very often we are seeing what is the remainder obtained when 7 power 85 is divided by a prime number, say 41. Some type of questions are being seen at set and net. For this, some adoption is there, some methodology is there. So what you have to do is, while evaluating a power k modium, we find a power k in terms of exponential terms, in terms of powers of 2, and computing the powers of 2 successively by squaring the previous terms. This is the methodology. So this is called exponential method. You have to go on squaring the powers of 2. For example, I want to compute the remainder obtained when 7 power 85 is divided by 41. Here, let us look at the powers of 2. See, you know, 2 power 0 is 1, 2 power 1 is 2, 2 square is 4, so on and so forth. 2 power 6 is 64, and 2 power 6 is 64. Just you add up one more power. 2 power 7 is 128, but certainly this 128 is larger. This is bigger than 85. So you may have to stop here. So will you express this power 85? This 85 is expressed as the powers of 2, possible powers of 2. First of all, write 85 as, generally any layman can write, say 64 plus something. What is the something? 21. Again, this 64, you express this 21 as possible powers of, sum of powers of 2. What is that? 16 plus 5. Again, is it possible to split 5 as sum of powers of 2? Let us see. What is that? This is again 4 plus 1. So likewise, you can express in total this 85 as 64 plus 16 plus 4 plus 1. I am rewriting, that is 1 plus 4 plus 16 plus 64. What I mean to have is 1 is 2 power 0, 4 is 2 square, 16 is 2 power 4, 64 is, as I told, 2 power 6. Now let us evaluate 7 power 85 mod 41. How I can express 7 in terms of 85? As I explained, 85 is sum of 1 plus 4 plus 16 plus 64. You write this as 7 power 1 plus 4 plus 16 plus 64 mod 41. Now you evaluate separately. But you know, mental calculation is required. But for explanation, I am giving in detail. 7 power mod 41 is only 7. 7 square mod 41 is 49. Already make use of previous one. 7 into 7, that is 49. It is leaving the remainder 8. Similarly, compute whatever we require. 7 power 1, 7 power 4, 7 power 16, 7 power 64. Likewise, go on applying and find the remainders as 23, 37, 16, 10, 18. Then you evaluate the 7 power 85 mod 41 as 7 power 1 plus 4 plus 16 plus 64 mod 41. You calculate separately. First one is 7 into 7 power 4 into 7 power 16 into 7 power 64. You know, 7 power 7 is 7. 7 power 4. 7 power 4 congruent to mod 41, whose result is seen to be 23. Already it is calculated. And remaining are also calculated earlier. So you make use of the product as 161 and 288. So a little bit calculation, mental calculation is also needed. So that product is turned out to be 38 mod 41. So finally it is resulted as a 38 mod 41. In between, some simplifications I gave on the right side. That is 161 mod 41 is only 38, and even 288 mod 41, it is leaving the remainder 1. The product of them is 38 into 1. So finally, the remainder obtained when 7 power 85 on divided with 41, that is a prime number, it is resulted as 38. So otherwise, you need to multiply this 7 power 85 as 7 into 7 into 84 times, and again dividing with 41. That is a very Herculean task. So this is somewhat, this is adaptable procedure, but still I want to make use of a little, I want to reduce that hardship to the extent possible by making use of certain theorems. They are the evaluation of Fermat's theorem and little Fermat. So what does it say? If P is prime and A is an integer not divisible by P, means they are relatively prime to each other, whose GCD is 1, then A power P minus 1 is congruent to 1 mod P. That is, on dividing A power P minus 1 with P, you are getting the remainder as 1. So in the below I wrote one more. Furthermore, for any integer A, we have A power P is congruent to A mod P. This is actually called as a little Fermat theorem. So how does it come? That is on multiplying both sides with A for the little Fermat's theorem. As a consequence, we are able to pick up little Fermat theorem. See, for example, I want to see an example. What is the remainder obtained when 2 power 340 divided by a prime, say 11? So this is a big calculation. By making use of Fermat's theorem, it can be easily calculated. 11 is prime and 2 is an integer whose GCD is only 1. First of all, you see 2 power 340 is 2 power 10 whole power 34. Then I am keeping P as 11, A as 2. And by making in little Fermat theorem, substitute 2 power 10 is congruent to 1 mod 11. 2 power 10 is congruent to 1 mod 11. I am raising to the power of 34 both sides. If you even raise it to the power of 34, still you are getting the remainder. 1 power 34 is only 1. So on the whole, you can say 2 power 340 when divided by 11, it is leaving the remainder 1. So I want to give some more examples. For example, what is the remainder when 2 power 50 is divided by 17? So had it been used by even the sum of powers, unlike in earlier method, it would have been taken some time. But now to taking less strain by making use of Fermat theorem or little Fermat theorem, it can be easily solved. And in between, you can write 2 power 50 as 2 power 16 into 3 plus 2. You remember, we are again making use of division algorithm. 50 can be expressed as 16 into 3 plus 2. Again, in turn, it can be written as 2 power 16 whole power 3 into again 2 power 2. So already, on the just a step above, 2 power 16 is congruent to 1 mod. P means here 17. So 2 power 16 is congruent to 1 mod 17. So even its power is also congruent to 1 mod, means it leaves the remainder only 1. So you are getting 1 power 3. So 1 power 3 into 2 square. 2 square we are getting as 4. 4 mod 17. 4 is a number which is lesser compared to 17. So on the whole, it is leaving the remainder 4. So this is a simple application of Fermat theorem. Even you can see what is remainder obtained. Usually it will be asked in CSR and set questions. What is the remainder obtained when 4 power 532 is divided by 11? So thing is, on putting P is 11 and A is 4, by making use of this Fermat theorem, 4 power 11 minus 1, namely 4 power 10 is congruent to 1 mod 11. But again, you have to make use of division algorithm, namely 532 you can express as 10 into 53. You have to divide with, it can be expressed as 10 into 53 plus 2. That is, in turn you can write 4 power 10 whole power 53 into 4 square. But already on putting P is equal to 11, in a Fermat theorem, it is resulted as on the above step 4 power 10 is congruent to 1 mod 11. So 4 power 10 whole power 53 is also congruent to 1 mod 11. That is, it leaves the only remainder 1. And what is remaining? Remaining On the next right side is 4 square. 4 square is 16. 16 on dividing with 11, it is leaving the remainder only 5. So overall you can say that the remainder obtained when 4 power 532 is divided by 11, it is giving the remainder 5. So these are only simple applications of Fermat theory. So now we are coming across an important aspect which plays a vital role in RSA algorithm in cryptography. You will be witnessing in the next session. So for this, these are some fundamentals. I am taking Zn set of all integers, positive integers, they are running from 0 to n minus 1, denote with Zn. Zn star is set of all numbers which are relatively prime to n, and phi n is the number of elements in Zn star. Phi n means this is known as Euler-Tocient function. And if n is prime, I can say that phi n is n minus 1. I will give some examples. And for example, I am taking Z10. Z10, I discussed earlier in addition modulo. Zn, it runs from 0 to n minus 1. So Z10, it runs from 0 to 9. Then what is phi n? The numbers which are less than 10 and which are prime to 10. How many number of numbers are there in Z10 which are prime to 10 and which are less than 10? I also explained this in the earlier slides. So they are namely 1, 3, 7, 9. So let us investigate some more examples. So once again I am explaining what is phi n. Phi n stands number of integers which are less than 1 and which are prime to n. That means they lie between 1 to n minus 1 and they are relatively prime to n. For example, 5, 4. How many number of numbers are there which are less than 4 and which are prime to 4? There are only 2, namely 1 and 3. You remember once again, 1 is a number which is less than 4 and relatively prime to 4, means GCD between 1 and 4 is 1. Similarly, 3 is less than 4 and GCD between 3 and 4 is 1. Why can't you ask that 2? Can it be relatively prime to 4? No. So in between, you may ask why we cannot take 2. I cannot take 2. Why? Because the GCD between 2 and 4 is not 1. So 2 divides 4. So only you have to take the numbers which are less than 4 and which are prime to 4. So they are only remaining 2, namely 1 and 3. Similarly, I want to take number of integers which are less than 5 and which are relatively prime to 5. So what are the numbers which are less than 5? I can take 1, 2, 3, 4. I cannot take 5. As per my theory, numbers, they have to lie only between 1 to n minus 1. So all these numbers, they will be less than 5 and which are relatively prime to 5. Why? Because GCD between 1 and 5 is 1, GCD between 2 and 5 is 1, GCD between 3 and 5 is 1, GCD between 4 and 5 is also 1. You observe one important fact. When n is prime, I gave in the previous slide, when n is prime, phi n is found to be n minus 1. So here also phi 5. When n is 5, phi 5 is found to be 4. Similarly, you can take phi 6. How many number of numbers which are less than 6 and which are prime to 6? There are only 2, namely 1 and 5. Similarly, I want to take phi 7. I need not calculate. Straight away I can tell. I know phi n is n minus 1. So I can write phi 7 as 7 minus 1. That is only 6. So these things, they are coming from Euler-Tocient function. They play a crucial role in RSA algorithm, where public key and private key are there in cryptography. So I may have to say one more, a conjecture. If m and n are relatively prime, then I can say that phi mn is phi m into phi n. For example, phi 15, I can express 15 as a product of two distinct primes, that is phi of 5 into 3, where GCD of m and n is 1, GCD of here 5 and 3 is 1. So phi 5 straight away I can write You just look at the first box. I want to evaluate phi of 15 by making use of the formula which is given. Phi mn is phi m into phi n. In place of m, I can take 5. In place of n, I can take 3. So according to formula, phi mn is phi m into phi n. So I can split into phi of 5 into phi of 3. So already we know phi of p is p minus 1. When n is prime, phi n is n minus 1. So phi is 5 minus 1, 4. Phi 3 is 3 minus 1, that is 2. So I can write this as 4 into 2, that is resulted as 8. Similarly, I can find phi of 165. So likewise, you can find the product of distinct primes. Whenever GCD between m and n is 1, I can write phi of mn is phi m into phi n. So with the result of this, Euler's theorem or Euler's theorem is originated. This Euler's theorem is a generalization of Fermat's theorem. So on keeping n is prime, I can generate Fermat theorem from this Euler's theorem. So it plays an important role in RSA algorithm. It goes like this. If GCD of n is 1 and whenever a is less than n, then I can say that a of phi n is congruent to 1 mod n. See, remember, I am not imposing any condition on this n. When n is prime, say n is equal to p, it will become a of phi p. But you know what is phi p? Phi p is p minus 1. So from this, you can generate Fermat theorem. In other words, Fermat theorem is a particular case of Euler's theorem, or Euler's theorem is generalization of Fermat theorem. So in other words, I am explaining if a and n are relatively prime, with a being the smaller integer, then when we multiply a with phi n times and divide this result by n, then you will be obtaining the remainder as 1. So let us give some illustration. I want to test Euler's theorem by taking a is equal to 5 and n is 6. What is the condition here? The GCD between a and n should be 1. A is less than n and GCD between a and n should be 1. So I am taking a is 5, 5 is less than 6 and GCD between 5 and 6 is 1. And remember, I am not taking n as a p. I am taking any integer. Then let us investigate the terms in Euler's or Euler's theorem. Then I need to compute phi of n. Here we are having a power phi n on the left side. So I need to calculate phi 6. Phi 6, as I explained, it can be written as phi of 3 into 2. Both are primes. Phi 3 is phi of 2 into 3, you can say. So phi of 2 into 3 is phi 2. Phi 2 is 2 minus 1. Similarly, phi 3 is 3 minus 1. So it will be resulted as 2 minus 1 into 3 minus 1. That is 1 into 2 is 2. So left side is a power phi p, a power phi n. So I want to calculate phi power phi of 6. That is phi power phi 6 is found to be 2. That is phi power 2 is 25. And I want to investigate. I want to trace out whether a power phi n leaves the remainder when it is divided by n or not. Let us see. So I got phi power phi 6, that is 25. I need to divide this 25 with 6. So it will be resulting as only 1. Even you can apply here division algorithm, or straight away you can see that this 25 is leaving the remainder 1 on divided by 6. So this is the verification of Euler's theorem. It plays a major role in RSA algorithm, where you are going to see some glimpses in cryptography in the later session. So I want to see one more set of slides. Where you are seeing the Chinese remainder theorem. So why should I study Chinese remainder theorem? So I should study Chinese remainder theorem in order to solve simultaneous linear congruence. Whenever more than 2 are there, 3 are there, I want to make use of Chinese remainder theorem. That is the advantage of Chinese remainder theorem. So in the long back, one was a proverb or some notation was there as per Chinese mathematicians, that is called sun to problem. There was a bag. In that bag, there were certain things whose total number is not known. When divided by 3, it leaves the remainder 2. When it is divided by 5, it leaves the remainder 3. And when the same number is divided by 7, it leaves the remainder 2. How many total number of things are there in a bag? For example, you are going to market, you are bringing some tomatoes, full of tomatoes in your bag. You are keeping tomatoes in terms of 3, but at last you are finding 2 tomatoes in your bag. So by picking in terms of 3, you are seeing at last 2 tomatoes. If not, you are picking in terms of 5 tomatoes in each group, but still you are finding 3 tomatoes are left in your bag. If not, you are grouping in terms of 7 tomatoes, but still you are finding 2 are left behind in your bag. How many total tomatoes are there in your bag? So that is a puzzle. This can be put in the form of mathematical linear congruences, that is called Chinese remainder theorem. You can adopt. So let us solve in terms of mathematical representation. It can be represented. X is congruent to 2 mod 3, the first one. Why? It is leaving the remainder 2 on divided by 3. Similarly, it is leaving the remainder 3 when it is divided by 5. Similarly, it gives the remainder 2 when it is divided by 7. So this is the mathematical formulation of the given word problem. This can be solved by Chinese remainder theorem. Just I am giving only statement due to paucity of time. Everywhere you can see its proof. Assume m1, m2, mk are positive integers. They are pairwise relatively prime, as I explained in slide number 1 in the morning. Then suppose a1, a2, so on, ak are set of any arbitrary integers. Then the system of linear congruences, say x is congruent to a1 mod m1, x is congruent to a2 mod m2, so on, x is congruent to ak mod mk, just like you have seen. It leaves the remainder so on and so forth. When on divided with the first one, it leaves the remainder 3. When on divided with 5, it leaves the remainder 2. When on divided by 7, likewise, you will be having so many number of linear congruences. Then you can write this x will be congruent to a1 m1 y1 plus a2 m2 y2 plus so on, ak mk yk whole mod m, where capital M is product of m1 m2 so on mk. In this case, mi is equal to m divided by small mi, and you have to solve this congruence. Say capital Mi yi is congruent to 1 mod mj for n is equal to 1 to k. Same problem I am solving. X is congruent to 1 mod 5, x is congruent to 2 mod 6, x is congruent to 3 mod 7. So what I need to find is m value. What is capital M value? I told in the theory, capital M is product of small m1, small m2, small m3. Here small m1, small m2, small m3 are 5, 6, 7, and which are relatively prime to each other. So 5, 6, and GCD between any two integers is 1, and in fact their product is found to be 210. So what you have to do is you have to find each capital Mi by taking capital M divided by small mi. So first of all I want to find capital M1, that is first capital M1, that is capital M. So it is wrongly printed. That is capital M on right side, capital M by small m1. That is 210 by, what is small m1? Small m1 is only 5, first mod value. That is 5. 210 on divided by 5, it is resulting as 42. Similarly, find capital M2. Capital M2 is capital M by small m2. That is 35. Capital M3 is capital M by small m3. That is resulted as 30. So according to this Chinese remainder theorem, you need to solve. Again, the knowledge of congruence theory, Euclidean algorithm, and inverse modulo, it plays a crucial role. That is, you have to solve this. Capital Mi, yi is congruent to 1 mod mj, you need to solve. So first of all, I am taking, so first one on keeping m1 as 42.
42 y1 is congruent to, as per this theory, 1 mod mj. That is first value I am taking modulus as a 5. The first congruent value is 5. So I am solving the first congruent value. 42 y1 is congruent to 1 mod 5. The thing is, what is the remainder when 42 is divided by 5? It leaves the remainder 2. So 2y1 is congruent to 1 mod 5. In other words, y1 is congruent to 2 inverse mod 5. So what is inverse of 2 mod 5? You have to look at mod 5 table. So obviously the inverse of 2 is only 3. Why? We got 2 3 is 6. 6 when divided by 5, it is leaving the remainder 3. So what is the first value of y1? 3. Similarly, I am taking second value. On taking second value m2 as 35. Again I am approaching the second congruence. mi yi is congruent to I mod mj. Take here mj value 6. Capital M2 value. M2 value is found to be 35. So I want to solve 35 y2 is congruent to 1 mod 6. Simply divide 35 by 6. What is remainder on left side? 5. Anyhow, 1 is there. 1 is less than 6. There is no change on right side. So only change is applicable to left side. On division of 35 with 6, it is leading to 5. And you can write 5 y2 is congruent to 1 mod 6. Then there are several methods. You may write y2 is congruent to 5 inverse mod 6. Or still you can multiply both sides with 5. So 5 into 5 y2 is also congruent to 5 mod 6. That is 25 y2 is also 25 y2 is congruent to 5 mod 6. But you know, this y2 will be congruent to either you may take 5 inverse or this 25 y2 is congruent to certainly 5 only. Why? Because 25 on dividing with 6 is leaving the remainder 5. Anyhow, by taking any method, you are getting this as only 5 mod 6. Similarly, I want to solve the third puzzle. That is the third congruence. 30 y3 is congruent to 1 mod 7. How it is arrived? On taking m3 value 30. And what is the small m3? Small m3 value, this 7. So I want to solve 30 y3 is congruent to 1 mod 7. You divide 30 with 7. What is the remainder? 2. So you need not divide right side, only 1. 1 which is certainly less than 7. So 2y3 is congruent to 1 mod 7. But I need to find y3 value. What is y3 value? That is the inverse of 2. So what is inverse of 2 mod 7? That is certainly 4 only. So as we discussed at the length in the last slide. So overall you are getting phi 3 value as only 4. That is 4 mod 7. So now you adapt the formula which is given earlier. X is equal to a1 m1 y1 plus a2 y, m2 y2 so on and so forth. But we are taking only 3 congruences. So you need to take 3 calculations and 3 sums. Namely a1 m1 y1 plus a2 m2 y2 plus a3 m3 y3. So we are getting this sum of products as 836 mod 210. But still, you know, 836 is larger, greater compared to 210. So it leaves the remainder 206. 206 mod 210. So overall, what I can say is with this problem, so in total, how many tomatoes are there? I am keeping 5 at a time from my bag. It is leaving the remainder 1. Only 1 tomato is left in my bag. I am keeping in terms of 6 group. Still 2 tomatoes are left in my bag. I am keeping in terms of say 7 tomatoes group. Still 3 tomatoes are left in my bag. Totally, how many tomatoes are there in my bag? The result is 206 tomatoes are there. So this is a simple application of Chinese remainder theorem. One more problem is given. You can see later. So with this, I want to stop.
Okay.
So thank you one and all for giving me this opportunity and for your patient listening.
Thank you, sir. Shall we start the question answer session now?
Yes.
1 minute. As we are having shortage of time, we'll go with few questions.
Yes.
The first question we got here is from Alfonsa Pratibha. Find the smallest positive integer that is congruent with minus 39 modulo 53.
See, minus 39, you need to divide with 15. So instead of dividing with 15, you go on adding till you get a positive remainder. So you go on adding like minus 13 plus 39 plus 15. Again, minus
Sir,
39 plus 15.
53, sir. Minus 39 modulo 53.
See, that's what I am telling.
Okay.
So just we add this minus 39 plus 53. Just what is the remainder you are getting? This is only 14. 14 mod 53. That is the only remainder.
Okay.
If not, we can do one thing, madam. They can be posted in one this one, and later on they can be answered. If they are oral, they can be answered. If it is problematic,
Okay.
we can solve later. They can
Sir, you can share white screen, sir. Whiteboard. You can write on that one with mouse. Stop the screen share and share whiteboard, sir.
Mamta madam, please proceed with the next question.
Yes, sir. Yes, sir.
Better you may ask next one also. No problem.
What are the major areas that we need to focus on to get in depth of cryptography?
So as I mentioned earlier, there are various mathematical backgrounds are needed, especially in number theory. One has to study divisibility properties, as I mentioned, Euclidean algorithm, and then congruences, as I discussed, the properties of congruences, and even Fermat theorem, Euler-Tauschent function I discussed.
Yes, sir.
And even Chinese remainder theorem. All these things, apart from these things, we may have to look a little bit of finite fields from algebra. That is also somewhat needed in cryptography.
Okay, sir. We have a question from Sharda Patel. Can you mention the practical use of this theorem?
Chinese remainder?
Maybe, sir. They have not mentioned the theorem.
Yes,
maybe
yes.
the last one. Yeah.
Same thing. Just now I have explained in the previous one of our slides. See, when you are going to a market, you are taking full of apples. You are keeping 4 at a time. Still you are finding one apple is left. You are keeping 3 at a time. 2 apples are left. You are taking 5 at a time. Some 6 apples are left. So these are coming under solution of linear congruences. So they can be formulated in terms of mathematical modeling. The set of simultaneous linear congruential equations, they can be solved by making use of Chinese remainder theorem. So that is one of our practical discussions, as I explained in one of our previous slides.
Can I ask the next question? Yeah. Is any specified book or for the basic things to be learned for reference?
Reference books, Button book is there. That is Number Theory by Button, and then Apostle book. Apostle, where it covers both elementary as well as algebraic and then prime number theory. So these are main books which are useful for UG as well as PG students. So apart from this, you can see some more material from available in the net, especially from reputed universities, Stanford, Oxford, and other universities. They are giving some notes.
Okay, sir. Now I come back to the closing of this question
Ma'am,
answer session.
ma'am, can I ask one question, please?
Okay, sure.
Can you permit me?
Hello.
Yes, sir. Please proceed.
Good afternoon, sir. This is Amarnath from CBIT.
Sir, good afternoon.
yeah, just you have said that Chinese remainder theorem for linear equations.
Yes.
Is there any theorem are similar to for nonlinear equations for solving two or more variables?
Non-linear means you have to see again quadratic congruences.
Yes, sir, like that.
Yes.
Quadratic and cubic.
Yes. Where we need to some other theory like that is somewhat different. As of theory goes, most of the people for solving linear congruences and a set of simultaneous linear congruence, they are using Chinese remainder theorem. But we need to see some more Euler's theorem and some other theory is there for solving quadratic congruences, Legendre symbols, and then Gauss lemma also useful there, and then quadratic reciprocity is law. Quadratic reciprocity law is there for solving quadratic congruences, especially having higher powers, especially power of 2, apart from these linear congruences, where you can see in Apostle book, especially.
Okay, sir. Thank you, sir. Thank you, sir.
Can I proceed further?
Yes.
Yeah. So we have come to the end of the question answer session. Now, I take the privilege of presenting the vote of thanks. On behalf of all the participants, organizers, I take the privilege of presenting the takeaways of today's session. The session started with basic concept of cryptography, which includes the process of encryption and decryption. We have been introduced to Euclid's algorithm, its extension, modulo operator, and its congruence. You have slowly laid a strong foundation for the study of cryptography by revising all the basic concepts. You have strengthened our basics for which we will be using all that in our next session. Interesting topics which pulled everyone's attention were Fibonacci number and golden ratio and their applications in nature. Sir, you have taken great efforts to explain the topics in a crystal clear way. From a simple topic, you slowly elevated us to complex concepts like Chinese theorem. Behalf of the Department of Mathematics, CBIT, I thank you, sir, for such an excellent elaborated talk. Thank you. Thank you, one and all.
Thank you, Srinivas, sir.
At the outset, I would like to thank one and all for giving this opportunity, especially the management of CBIT, the principal, head the Department of Mathematics, and other colleagues of the department, teaching and non-teaching staff, and also the participants. Thank you, one and all.
Thank you, Srinivas, sir.
Yes. Now I
Okay,
request
sir,
all
welcome.
the participants we will be proceeding as per the schedule. We will be having a break now. Thank you.
Suresh.
Suresh, can you hear me?
Hello. Hello. Hello.
Hello. Gordon sir.
సురేష్ సార్ ఎస్సీ సారే ఉన్నట్టుంది. సార్ వీడియో ఆన్ చేయండి ఒకసారి. వీడియో ఆన్ చేసుకొని అన్మ్యూట్ చేయండి.
సారే చేయాలి అది.
ఓకే
చేసినాను.
చేశాడు సార్ చేశాడు.
సార్ గుడ్ ఆఫ్టర్నూన్ గోవర్ధన్ సార్.
Please. Hello. So
good afternoon everyone.
Yeah.
I welcome all the participants for the second session. My name is Dr. Swatmaram, working as an associate professor in the Department of Mathematics, CBIT. It gives me immense pleasure to introduce Dr. C. Govardhan, a mathematician, a great teacher, a humanitarian. I sincerely thank Dr. C. Govardhan, sir, for accepting to speak at our seminar. Dr. C. Govardhan is an associate professor in the Department of Mathematics, Usmania University. He did his post-graduation from Usmania University and received Professor N.V. Subbarao Memorial Gold Medal, HEL Gold Medal, Indian Mathematical Society Gold Medal by Usmania University. He also received CSIR Fellowship and completed his PhD from Usmania University. He has 30 years of vast teaching experience and guided many students to get CSIR and JRF scholarships in the Department of Mathematics, Usmania University. He has also published books on topology, measure theory, complex analysis, number theory, real analysis, mathematics and statistics, Telugu Academy Mathematics books for intermediate, and also state government mathematics textbooks for class 6 to 10th. Dr. C. Govardhan has successful administrative experience. He has served in many administrative positions such as principal, additional controller of exams, chairman board of studies, etc. As a chairman board of studies, he has contributed a lot in the development of curriculum and syllabus of PSC and MSc computer science courses. Also, he conducted several training programs for computer science teachers at UG and PG level. This session is of great value addition to today's seminar. Now I request Dr. C. Govardhan sir to take over. Sir, please.
Swatmaram, thank you for your nice words showered on me. First of all, let me congratulate you for organizing such a wonderful seminar. And I also thank you all, Raj Reddy, Mr. Ganesha Rao, Suresh, Swatmaram, Sridhar, Kiran, Amarnath ji, Mamta madam, Sharda madam, Padma madam, for giving me this wonderful opportunity to speak to the participants. So I'm given 2 sessions in this program. One session is devoted to look into RSA cryptography, and the other one is devoted to elliptic curves. And earlier speaker, Mr. Srinivas, spoke so many things about number theory. Number theory forms a basis for all these cryptography procedures, protocols. And when we look into prime numbers among the natural numbers, the story of prime numbers is quite romantic. There are so many funny things to be spoken about prime numbers. And I want to look into a few points first with regard, before giving my presentation. I want to look into a few more aspects of these prime numbers among natural numbers. Most of the things are already spoken by Mr. Srinivas, but I have a few more things to be spoken to the audience before entering into my main topic, namely RSA public key crypto system. And these are the first fundamental question is how many primes are there among the natural numbers? The list of primes in natural numbers is infinite. And this is observed by Euclid centuries ago. The proof that is furnished by him still valid. Same proof is there for the infinitude of primes, which is considered to be one of the jewels in the whole of number theory. And having known to the fact that prime numbers are infinitely many, surprising thing is that suddenly between two successive primes, you can notice the difference to be just 2, like 3, 5. If I take 5, 7, 5, 7, these are 2 primes which differ by just 2. The difference is 2. If I take 11, 13, the difference is 2. Such primes are called twin primes, right? So that means immediately after 11, there is one more prime with a gap of just 1 integer. Such primes we call technically twin primes. Nobody ever knows till today how many such twin primes are there. But this list, people feel that it's never ending. There are infinitely such prime pairs which differ by 2. But by contrast to this one, there is another important result, namely, you imagine any number k. I can produce a block of k consecutive composite numbers. For instance, if I take k is equal to 4, I can look into say 24, 25, 26, 27, 28. If I take k is equal to 5, I take k is equal to 5. I can have this many numbers consecutively, 24, 25, 26, 27, 28. We'll look into this. There are 5 numbers, each one of which is a composite number. You can notice it is the first one is divided by 2, it's divided by 5, third one divided by 13, fourth one 9, fifth one is divided by 14. So it's a block of 5 consecutive natural numbers, each one of which is a composite number. None of them is a prime number. You may surprise what's great in that, but my point is that you name any, not only 5, you take k to be some 1,000. I can produce 1,000 consecutive composite numbers, each of which is a composite number. So in other words, I can produce a block of 1,000 composite numbers, and which are consecutive. So that means none of them is going to become a prime number. Spoken differently, between one prime to the next prime, sometimes it may happen that there is a gap of 1,000 natural numbers. So this you can look out something like this. You take 1,001 factorial plus 2, 1,001 or 10,001. Let's take 10,002, 1 factorial plus 2, etc. If I take like this, 10,001 factorial plus 10,001. If I take this, you can notice that each one of these numbers is a composite number. For instance, if you take the first number, it is divided by 2. Second one, it is divided by 3. Third one, it is divided by, last one is divided by 10,001. So each one of them can be seen to be a composite number. None of them is a prime number, you can see. What does this indicate? There are large blocks of consecutive numbers which are none of which is a prime number. So sometimes between 2 consecutive primes, there may be a large gap. Sometimes there may be a very small gap like 2, 11, 13. So therefore, if you look into the nature of distribution of primes among natural numbers, it's quite irregular. Irregular in the sense, but surprising. Sometimes very short difference will be there. Sometimes very big difference will be there between 2 consecutive primes. There is another interesting point. You start with any n bigger than 1, which is known with the name fundamental theorem of arithmetic. every natural number n bigger than 1 can be written as a product of primes. This is known as a fundamental theorem of arithmetic. So every natural number n is a product of primes, not necessarily, of course, distinct. And this, in fact, is called factorization of n into primes. Now, as is the case in every field, if you look into calculus, finding derivatives for the function is quite easy rather than finding integrals. Not every function can be integrated in the compact form, but every function can be differentiated in such a manner as long as it's continuous. Okay. Similarly, you can add two fractions, fx by gx plus f1x by g1x very easily. But when you are asked to find out the partial fractions of a fraction, it's tough. So you go through anything, any of these things. One way would be quite easy, the other would be quite tough. Similarly, if I take two numbers a comma b, finding product is a simple job. Whereas given any number n, factorizing this one into a into b is tough. So this is the whole heart which lies behind this PKC. So that means finding products is not a big thing for the computers, but finding factorization is a quite tough job. Just taking this into account, we can exploit this particular property to devise very strong crypto systems. And before even going for that, I want to make a mention about this function, which we call counting function. This is going to count the number of primes up to x. To start with any positive real number, up to x, this pi x is going to count the number of primes. If I take pi of 3.1, it is equal to 2 because there are two primes, 2 comma 3 up to 3.1. If I take pi root 15, how much is this? Root 15 is nothing but it's less than 4, right? Up less than 4 means 2, 3. These are only two primes that are available up to root 15. So it's going to count the number of primes. There is one interesting result with regard to this, which is known with the name prime number theorem. So can we count the number of primes up to x? There is an estimation by prime number theorem, which is close to this one. In fact, earlier speaker spoke about this one. A better approximation to this one is already known to you by the earlier speaker, namely log x minus 1. Of course, here it is natural logarithm. So this is going to give you a better estimate for large x. It is not true for smaller ones. For large x's, it is true. So when you deal with very big numbers, I think the difference between pi x and this x by log x becomes very, very small. In other words, this limit x tending to infinity, pi x by log x, this is going to become 1. So in other words, as you increase this x very large, and this pi x is going to become very, very close to x by log x. Spoken differently, roughly you can count pi x to be approximately x by log x when x is large, right? When x is large. Right then. But this is one important point which has to be kept in mind while looking at this RSA crypto system. Shall get back to the RSA crypto system. How is that this is going to? These things are going to play a dominant role in the whole of this crypto system. Now, this RSA crypto system, of course, it's mainly devised by 3 people, Rivest, Shami, and Yadelman. And this has come into light in a paper published by them in 1978. I think that made waves in the mathematical circles. And since then, in fact, it's playing a dominating role in the cryptography. And we shall try to look at this RSA public key crypto system. RSA public key crypto system. What do we mean by public key crypto system? If you look into any crypto system, you have a space containing messages, a space containing keys, a space containing ciphers, and all these things, right? In the public key crypto system, we will have a key to encrypt and we will have a private key to decrypt. As is the case with any crypto system, we will have some function to encrypt a message, and to decrypt the message, we need to go for its inverse function, and that has to be made use to decrypt the message. So what makes this particular RSA secure when we want to communicate over insecure channels? The point is this one. Encryption becomes a bit easy, but decryption is very, very tough. So how come this is done? Now we shall start with the procedure of this RSA in the following chart, and wherein we make use of these two fictional characters, Alice and Bob, where they want to communicate with each other over insecure channels, and they want to make use of this RSA. What is that they have to do? So this RSA crypto system involves 3 steps in it. One is key creation, and the other encryption, and then decryption. Suppose Alice wants to send some message to Bob by using this RSA. What is that they have to do? First, they have to make out a key creation. For that, what they do is they agree on 2 secret points P and Q. They choose 2 secret points P and Q, and choose some encryption exponent E, which makes GCD 1 with the P minus 1 into Q minus 1. And this E, which is making GCD 1 with P minus 1 into Q minus 1, has encryption exponent. And this particular capital N, which is the product of P and Q and E, this pair will be made public. So this N comma E will be in the public knowledge, and this will be there in the public directory. So anybody who knows these 2 numbers, so they can encrypt any plain text. Remember, plain text in sense, you take any text, you convert that into binary numbers, and then go to the decimal equivalent, and then convert that into cipher number equivalent, and then convert that back into binary equivalent, and then you can get back to plain text. That is the process which goes on with usual standard coding schemes. So let us consider plain text here is there as a number in the decimal system. So what do they do is, Alice, she wants to send some plain text M. Plain text M in sense, it is the decimal number corresponding to the plain text message to be sent to Bob. So we'll be starting here at M, right? If this plain text is to be conveyed to Bob by Alice, what does she do? She makes use this public key N comma E, and she computes M to the power of E modulo N. I think this modulo N operator, you know, its meaning is nothing but when M to the power of E is divided by N, whatever the remainder comes, that remainder is nothing but C. That's the meaning. So M power E modulo N means it is the remainder when M power E is divided by N. If that is C, C is the cipher text which is to be sent to Bob. So Alice, she computes this C. So this C then will be sent to Bob. Then how does he decrypt Bob, having received the C from Alice? So now, what does he do? Remember, these P and Q primes, which are secret, and the product is revealed to the public, not the individual factors P and Q. But these are 2 primes which are there in the knowledge of both Alice and Bob, right? And having received this particular ciphertext C from Alice, Bob then tried to find out some decryption exponent, namely D. The decryption exponent is nothing but that is the number which satisfies this congruence. E into D congruent to 1 modulo P minus 1 into Q minus 1. And this is called in the congruence theory as an inverse of the encryption exponent E with respect to the modulus P minus 1 into Q minus 1. Because P minus 1 Q minus 1 is known to Bob, he can compute this D easily. And theory of congruence guarantees such a unique D. Having computed this D, then he computes C power D modulo n. It means he raises C to the exponent D, this much power. When this divided by n, the remainder is observed to say m prime. Then this m prime is nothing but the plain text n. So this is what is going to take place between Alice and Bob. The channel over which they are exchanging their messages may be vulnerable to attacks by enemies. Still, there is no problem. And they can send such a C, and that man Bob decrypts the message by computing C power D modulo n, where D is the solution of this congruence. PD congruent to 1 modulo P minus 1 into Q minus 1. But there are several points to be noticed in this small simple procedure. This becomes tough, this becomes secure only when P and Q are very large. That's one thing. P and Q are very large, and preferably both of them are of almost same size. When the number n is very large and there are P and Q are of same size, then this particular communication becomes a bit secure. But when the numbers are very small, it is not going to be that secure. That's what one has to keep in mind. Let us exemplify this particular method with some examples. Right? Let's go to one example. So we shall illustrate the whole procedure that has gone in the previous chart with a numerical example. So let me choose two primes, P and Q, P to be 1223, Q to be 1987. Both of them can be checked to be primes. And compute capital N 1223 into 1987, which is 2430101. You can check through simple calculator, or you can compute. And then we have to choose an encryption exponent E. It can be anything which is going to make GCD 1 with P minus 1 to Q minus 1. You can observe that this 948047, 2426892 is 1. This will also be made public. So this public key becomes now this N along with this E. So this is public key. So anybody who knows this pair can encrypt the message. But decryption is a bit tough, because that requires the knowledge of P and Q. That requires factorization of n. Factorization of n into product of primes is very tough. As long as that is tough, I think it's going to be secure. Right? Now try to look into a plain text M 1070777. Better to choose this M to be of size smaller than n. Suppose your message happens to be bigger in size than n. Then what you have to do is you have to make that into blocks of sizes lesser than n. Suppose your message M is bigger in size than n. Then break that M into blocks M1, M2, etc. Mk, where each Mi is smaller than n in size. And each block has to be separately enciphered. And then that blocks of enciphered numbers are to be sent to the intended person. Right? So nothing to worry about that. So for the sake of simplicity, let us take M to be smaller in size than n. Let me take this to be the message to be sent. And we shall make use the key, public key n comma e, to compute ciphertext. What is that you have to do? You have to compute n power e modulo n. M here is 1070777. N ciphering exponent is nothing but 948047. Modulo capital N is this. So this, of course, how to compute such a bigger power modulo this number? You may be wondering. I have made you some calculators available on the various stores, either Apple Store or Google Play Store. You can find out some calculators. Zering calculators can be used to compute this modular arithmetic. Such a large powers can be computed by using a modular arithmetic calculator, like arithmetic calculators. So my C becomes so much. So the C will be sent to Bob. The C will be sent to Bob, and having received that message from Liz, Bob then computes D by using this formula, ED congruent 1 modulo P minus 1 to Q minus 1. Because Bob knows P minus 1 to Q minus 1, I think finding D is nothing but finding a solution of this congruence, right? Again, this congruence is nothing but to find inverse of this number modulo this number. Again, same modular arithmetic calculators can be made use to find out this D. And then having got this D, you take that ciphertext and erase that to the power C power D modulo n. That is going to result in 1070777, which is the original message sent by the Bob, Alice to Bob. Okay, this is what's happening. But here, okay, even deciphering also requires computation of large powers and computational solutions of such congruences. Exactly at this stage, Euclidean algorithm becomes important, and computational aspects are also there. Namely, you need to compute large powers. From the computer science point of view, these numbers are considered very small. Big numbers are numbers having hundreds of digits here. Remember, numbers having hundreds of digits are considered to be big numbers. Numbers having tens, 15, 100 digits considered to be very small. So therefore, computing these things also require a lot of time. So in the procedure, this calculation is called enciphering modulus, and E is called encryption exponent, and D is called decryption exponent, right? In this RSA public key crypto system. So here in the system, you look at this. In this, N, E, both of them are made public. Without revealing the factors of N. These are there with only Bob and Alice. They're not revealed to the public. Public knows only N and D, so that they can encrypt any message. But decryption is very tough. So unless this D can be found, you cannot decrypt that message. So unless some other trapdoor information is available for the enemy, they cannot reveal this particular D. They cannot get this D. So this D can be found only when this P minus 1 to Q minus 1 is known. But knowledge of P minus 1 Q minus 1 requires knowledge of P and Q, which is there only with Alice and Bob. As long as these P and Qs are very big and they are only with Alice and Bob, I think you can consider this procedure to be quite secure. Okay. Right. Having seen this, you can look at some problems, and I have made a mention about these problems. So for the sake of practice, you can compute them. These are going to be a good practice over these RSA PKC. They are not as it is same problems, but certainly these are going to give some good practice over computational aspects of that. So I have done some problems here. So if I take first one, x power 19 combined 36 modulo 97. If I compare this one with the x power e combined c modulo p, this 97 is a prime number, you can notice. If I take e to be the 19 and c to be 36, p 97. You can see that this 19 combined 6, GCD is 1. That is GCD e comma p minus 1 is 1. You can compute e into d to be this, which is the 91. So that this is going to give you the answer. So these computations you can do pretty easily. I'm not going into the details of that. If I take n to be 401227, it is again same RSA problem. It's a product of 2 primes 607 and 661. P and Q, P is equal to 607, Q 661. Both of them are primes, almost they're same size. So let's try to look at this. X power 389993 328047 modulo this one. Right? If I compare this one, I got my typical point is that my X is the message, and which is encrypted as 328047 by using this enciphering exponent or encryption exponent. E is this, C is this, PQ is this. So I have to reveal this X. This is X is my original message. What is it I have done? The original message X is enciphered to this one with encryption exponent 38993 modulo this N. So therefore, in order to get this X back, what is it you need to find? You have to break this 401 to product of 2 times P comma Q, which are known to be this one. Of course, in this example I have given you, but the party who are intended to decrypt that one, they should know on their own. That is very tough job. So therefore, this becomes P minus 1 to Q minus 1, 606 into 660, which is 39960. If you look into this GC of 38993 and this number, you can see that it's 1, the way I have chosen. So therefore, if you find D with this property, 38993, D come at 1 modulo 39960, then D is going to be, again, here I have made use that modular arithmetic calculator to find out this D. So once this D has come into picture, you can get back to your X. X is going to become C power D, namely this. I think this is the original message, which is encrypted as 328047 by using that encryption exponent. Even with some smaller Ds also, you can do this particular job. That's not the context for us. We shall skip that part. You can read out in the notes that I provide to you at the end of the lecture. So there is an alternate method to find out that. Now I would like to look at a practical example. Let's look into a practical example. Look at this secure communication over a computer network using RSA. I have taken the example of your CBIT only, and when I look into your CBIT website, and this SSL certificate reveals some information like this. If you open that website, HTTPS, which is padlocked with this one, if you click that padlock, and so much of information flows in that cbit.is.in website, wherein you can see there is a mention about public key in the form of this, and there is a mention about exponent. Exponent is to mean for encryption exponent that we have spoken in the RSA cryptography, and public key means public is capital N is this. So this whole number which is there in the hexadecimal system, this is our capital N. This is our capital N. And the encryption exponent E is 65537. 65537. And they have made a mention about this one in hexadecimal system because the number of digits happen to be less when I compare with the decimal system. Let us see what's happening with this. This is in fact public key. In fact, they have made use RSA encryption algorithm, and wherein that public key happens to be this N. This is my N. And that encryption exponent is 65537. Is this okay? Let us see what is there with this. If I look into that hexadecimal number given in the website, it's going to consist so many digits. What are the base digits of hexadecimal system? 0 to 9 along with A, B, C, D, E, F. So you can notice that the A, B, C, D, Fs are there, no more than A, B, C, D, E, Fs, along with 10 more digits, 0 to 9. So hexadecimal system, that number happens to be N equal to so much. When this is converted to decimal system, this number turns out to be consisting so many digits. In fact, number of digits here is 617 digits are there. So therefore, when you want to look into factorization of this N into PQ, where that number happens to be a 670 digited number in the decimal system, what amount of labor is required to factor that one we shall now see. Right? In that particular certificate, HTTPS certificate, there is a mention about RSA encryption, wherein the public key is mentioned with the N and E. We now see. So your N in decimal notation consists totally how many digits? 617 digits, right? And your encryption exponent, which was spoken there in the RSA, is nothing but 65537. Now, in order to decrypt an encrypted message, namely M, without the knowledge of that decryption exponent D, one will have only two options to break that. What is that? First option is to compute factors P and Q of n, or to guess prime factors P and Q such that PQ becomes n, right? Either you have to guess prime factors P and Q from among the available primes, or else you have to factorize this n into product of primes. These are the only two options left in order to decrypt the message in order to find that particular D. Then what amount of labor is involved, we shall observe. If I look into the option 1, capital N is a product of two primes, maybe around 300 digits each, because we have spoken in the beginning itself that the modulus term N is a product of two primes P and Q, which are of almost same size. Because the number here N happens to be a number of 600 digits, the primes appearing the factorization of N may be of size around 300 digits each, right? So even by using the most powerful factoring algorithms available till date, to factor such a number, it is going to take a prohibitive time. It's just impossible to find out the factorization in the real time. So it's going to take just prohibitive time, right? We shall see what if I try to guess for P and Qs, whether a prime number divides n or not. Once one prime divides n, you can look for another prime to be Q simply by taking n by P. So can you guess any P to divide this n? But in order to guess this P, what is to be done? We know that capital N, you know that this capital N is a product of two primes which are close to each other, very close in size. So that I can assume that the product, the primes that appear in the factorization of N may be primes having digits somewhere in between 250 to 350, we can assume, right? If I assume that the prime factors appearing in the factorization of N are of size having somewhere 250 to 350 digits, I think what is that you have to do? You have to guess for the primes that lie in between such gigantic numbers, right? Such numbers which are having 250 to 350 digits. So somewhere the primes in between such big numbers you have to guess, which are going to divide n. We shall see at least how many primes are there in between these two numbers. If I were to look into a rough estimate of numbers or the prime numbers between 10 to the power of 250 and 10 to the power of 350, it is approximately by using that prime number theorem which we have spoken in the beginning. It's going to become how much? Here x is this one. So prime numbers falling between m and n is nothing but pi n minus pi m for very large m and n's, right? And if that is the case, you have to look into pi n minus pi n. My n here is this, my m here is this. So let's try to compute this pi n. Then you call this one as n and this one as some n. So pi n minus pi n. Or you call this one as some x1, this one as x2. So pi x1 minus pi x2 should give you the roughly the number of primes falling in between those two numbers. So it's nothing but 10 to the power of 350 by log of 10 to the power of 350, which is 350 log 10, minus 10 to the power of 250 by 250 log 10. You can see that after simplification, this will be very close to 10 to the power of 347. What does this mean? Can you understand what the meaning of this one? It means that there are so many primes in between these two numbers. In between numbers having 250 digits to 350 digits, there are 10 to the power of 347 available primes are there, at least. At least so many primes are there. But remember, and from among them, looking for such big primes and testing for their divisibility, the divisibility of n by these primes, it's in fact very, very tough job. Very, very tough job. So therefore, guessing so many primes, which are so many in number, which are so large, it's just beyond guessing, right? So guessing the factors P and Q is very tough if you want to go for guessing. Factorization is also very tough. But if I were to choose any one of these two options, I am left with only first option. I think rather than the second option, first option looks all right. But first option is practically impossible. So practically impossible when your calculation happens to be a number which consists 4,000 or 2,000, it's of 256 bytes. When a number n is of 256 bytes, then this is going to become very impossible task with the present day computation skills available, or still latest and very powerful algorithms available. You know, only the powerful algorithm to factorize the natural number n till date is that prime field sieve method. That is the powerful factoring algorithm for any natural number n. Even by using that powerful prime factorization algorithm also, this becomes impossible to factor this, at least till today. But tomorrow this may be broken with some very powerful some other factoring algorithms. But the present day techniques reveal that it's just going to be impossible to break this when you are dealing with numbers having 256 bytes, right? But remember, in looking into this factorization of integers n, there in fact arise so many questions. While dealing with the RSA encryption, we need to compute GCDs, right, up to large numbers, for which you need a powerful algorithm to deal with. You need to factor a number into product of primes. That itself is a factorization problem, which is very tough. Even you need to check whether a given number is a prime or not. That primality testing is also very tough. And the only powerful sieve that is available to look into whether a number is prime or not, that prime field sieve only, that's very tough. But then there is another problem, namely to compute very large powers of large numbers modulo another large number. That also needs a lot of big computations. And another problem, how to find large primes. Of course, several groups are working to find out larger and larger primes. When you look into the beginning of the number theory, people used to compute bigger primes only for the fashion sake, for the hobby sake. And in fact, number theory was considered to be one of the hobby sciences rather than without any applications to the practical. Now that has become very important. It's finding applications in the cryptography, right? So there are so many primality checking algorithms, and still with the present day standards, breaking a key which runs into 256 bytes and whose expansion is going to lead to a number in the decimal system having 600 plus digits is unbreakable, at least till today's standards. Okay, so these are some questions which are associated with this RSA crypto system, right? But then I would like to pose two more important questions at this stage. Namely, one important question. If you look into this RSA crypto system, we already spoken in the beginning that you have to choose very large primes P and Q, which are almost of same size. The product n is to be taken, and you have to choose some encryption experiment which is going to make GCD 1 with P minus 1 to Q minus 1. That is taken as a public key, right? In this case, at least public key is going to be very large, right? Public key is very large, and to even messages also run very big when you are dealing with such big keys and big modulus term n, that becomes very big, right? So it's going to occupy space and time also. Uses time and occupies space. So time and space, okay, will be a problem. My question is this: rather, can we achieve time? Can we achieve space? Space in the sense Can we minimize the space to be occupied by a key? Can we devise a method which is going to take a smaller time or lesser time than RSA? More precisely, can we ever devise any other public key crypto system wherein these two problems are addressed? Namely, that the key should be small in size compared to RSA. That encryption business should also be very simpler, but decryption business should be very, very tougher compared to RSA. So making decryption harder compared to RSA, making encryption easier compared to RSA. Can we ever devise any public key crypto system? So in order to address this one, people have come up with another encryption or cryptographic algorithm that is namely elliptic curve cryptography. Elliptic curve cryptography is nothing but that's going to non-elliptic curves, and we shall take up that discussion in the next lecture, wherein we take up the discussion on elliptic curves and how is that these elliptic curves are made use, sometimes preferable over RSA to encrypt messages and decrypt messages. Okay, what type of techniques are involved in those elliptic curves we shall discuss in the next lecture. Shall we look into some questions from the audience? Hello? Swapnara? Hello? Sridhar?
Swatna?
Sir, please. Sir, please.
Suresh, can you listen to me?
Yeah. It will be better little louder, sir.
Shall we look for some questions from the audience? Any questions from the audience? Hello?
We will get back to you, sir. That we have to get the copy of that.
Okay.
After the end of the second session.
Okay. Shall we break for another session?
5 minutes, sir. Yeah.
5 minutes. What shall we do now?
If you want, we will break for 5 minutes, sir.
Yeah, let's give a break. If there are questions, I would like to attend them. Otherwise, we'll break for that.
Yeah, just I'll check with that.
You please check. So we are going to address this question to look for any public key crypto system that makes encryption easier and decryption still harder compared to RSA. That is nothing but elliptic curve cryptography.
Excuse me, sir.
Please.
There is a question from Komal.
Please.
Can I ask you?
Please.
If we notice first few primes, there is an alternative difference of 2 and 4 after the number 3. Is there any such pattern for higher prime numbers?
So that's a good question. That's what I was talking about. Komal, what is his name?
Komal.
Mr. Komal, it's a good question. The point is that the distribution of primes among natural numbers is quite surprising. Sometimes you can see immediately a prime with a gap of one number in between. Sometimes you can see very big gaps. There is no guarantee that with such and such gaps we can arrive at some other prime. Suppose if you prescribe some prescribed gap, that much gap can be assured. That's what I was telling you. There are blocks of composite numbers. You make a mention about any size, I can produce such a big block of composite numbers wherein you cannot find any prime number in between. So therefore, there are arbitrarily large gaps between two consecutive primes. That is what is noticed. But simultaneously, surprisingly, there will be some small gap between two consecutive primes, like twin primes. When bigger and bigger twin primes are also found, you can see them in the prime pages, which is spoken by earlier speaker. There is a web page which goes by the name Prime Pages, wherein you can see so many twin primes. So nature of prime numbers among natural numbers is quite typical, and we cannot say that immediately we are going to get some prime. So we cannot say that next prime is going to be within such a distance. There may be very big distance for the next prime. There may be very small distance from the next prime. If you want to go from one prime to the other prime. So therefore, I think there is no such typical formula to bind these relations. The only formula that binds prime numbers is prime number theorem. But for that, no other typical character can be seen with prime numbers, namely prime numbers up to x is going to be quite close to x by log x. For very large x, even that comparison does not work for small x's. That's the only thing people know till date. The behavior of prime numbers among natural numbers is quite irregular. No such formula, no such thing can be devised. As such, the next prime is going to be with so much of gap. Like this, you cannot see. But certainly, there are some large blocks of composite numbers. I think I have answered enough for the question.
Thank you, sir. And it's not a question, but Arfin, Rafiq.
Okay.
Please share PPTs as they have very valuable information.
Yeah, I'll certainly share. Certainly share, no problem.
Because he's saying it is a very valuable information with respect to the UGC net exams. He has mentioned.
I'll certainly send them, no problem.
Yeah. Thank you. Thank you.
Prime numbers do not have any formula. So they do not bind by any formula. So that's what we have to remember. Their behavior is quite irregular among natural numbers. That is making all these procedures to be very tough. Otherwise, everything becomes so easy, right? The moment factorization becomes easy, everything collapses. The moment there is a person finds a formula of prime numbers, that's easy. But both of them are next to impossibility. Next to impossibility from the number theory point of view. So that is going to make all this procedure to be very secure, right? Hello?
Sir, shall we break for 3-4 minutes?
Yeah, certainly.
Yeah.
Shall I end
back up after 5 minutes.
Okay. Share screen.
Ram,
Shall we
Sir,
begin?
shall we start the session?
Yeah, I'm ready. Okay. Hello.
yes, sir.
I'm starting. Okay.
Yes, sir. Yes.
So in the previous lecture, we made a remark. Namely, having seen RSA, we are trying to look for another crypto system. Another crypto system where is there any public key crypto system where encryption becomes easier and decryption becomes harder compared to RSA? I think that question can be answered by using this ECC, elliptical cryptography. What are these elliptic curves? How is that this elliptical cryptography is going to make that job? Namely, it's going to become quite easy to encrypt, very tough to decrypt, even when we compare with the RSA. How to look at that? So we shall first look into the definition of elliptic curves. An elliptic curve is nothing but it is the set of solutions of the equation in the form y square is equal to x cube plus ax plus b, where of course together with some extra point O, where the constant a and b are bound by the relation 4aq plus 27b square not equal to 0. Any such equation is called Weierstrass equation. Solutions of this Weierstrass equation, y square is equal to x cube plus ax plus b, together with some point O, we shall describe this in a bit later, satisfying the condition 4aq plus 27b square not equal to 0. This is called an elliptic curve. Remember, by definition, elliptic curve, it is neither ellipse when we look into its geometry, we are going to realize. It is not at all a curve, it is the set of points only, right? The name looks misleading, don't worry. So, such equations, which are called Weierstrass equations, they are called elliptic curves. So, an elliptic curve, E we mean, it's an equation of the form y square is equal to x cube plus ax plus b, where a and b are real constants satisfying 4aq plus 27b square not equal to 0. Preferably a and b are integers here. This number 4aq plus 27b square is called a discriminant of the elliptic curve E. Why we are putting this restriction in this equation? Very simple. I don't want to allow any repeated roots for the cubic x cube plus ax plus b. In case 4aq plus 27b square becomes 0, this cubic, namely x cube plus ax plus b equals 0, will admit repeated roots. And we call this number 4aq plus 27b square as the discriminant of E, denoted by delta E. Because deltas of xe, we shall call with the name discriminant of E. You can see that this discriminant becomes 0 only when this equation has got repeated roots. I think proof is not necessary for us, but very easy to see. And this equation 3 will have repeated roots. If you look into your calculus, this says that if 3 has a repeated root, say e, then eq plus ae plus b equals 0, and its derivative would also be equal to 0. When fx has a root alpha repeated, both fx and f dash x will have alpha as a common root. That's what I have applied. So if I make use these two equations, and if I remove e and b's, you can see that if I remove that e, you can get a relation connecting a and b as 4aq plus 27b square equal to 0. So therefore, this condition that we have laid down here is to ensure that right hand side cubic should not have any repeated roots, or should not have any repeated factors. That is what is ensured. But why we are putting that? I have got my own goals to meet in order to put that restriction. So, by the definition, what is the meaning of this an elliptic curve? An elliptic curve is nothing but its set of the points x comma y's, where the coordinates x comma y satisfy the relation y square is equal to x cube plus ax plus b, where a and b are integers satisfying 4a cube plus 27b square not equal to 0, together with some extra point o. I want to discuss this extra point o a bit later. For the moment, you agree to this, and I shall explain this in a bit later. Right? And what I do is, on this particular set E, which is set of points x comma y, I want to impose some kind of addition-like thing, which is going to make this set E to be a group. And don't worry about the definition of group. A group is a typical concept coming in the mathematics. Under this operation, if I add any two numbers, the resulting number goes into that. Under this operation, the operation is associative, and there is something like zero element which is there in the addition of real numbers, and there is some additiveness which is there in the negative of real numbers. If such conditions are there, in addition to that commutativity, we call such a thing to be a group. Don't worry that group is nothing but a set associated with some operation available with it, satisfying certain conditions. Conditions like whenever you take two elements from that, some should go into that. That operation should be associative, and zero-like element should be there, negative-like elements ought to be there. When these are there, we call it a group. And in addition to that, commutativity is also there. We say that it's a commutative group. What I do is, on this set E, I want to impose an operation called plus, which we write it as encircled place or ordinary place, doesn't matter. I want to define a special operation like plus on this set E, which is going to make this E a group. In fact, an abelian group. It's going to give us an abelian group. The question comes in how to define that addition. This addition is not just coordinate-wise addition, it is a typical addition. And before going for that, first we shall look into few examples. Let us take these three elliptic curves, namely y square is equal to x cube minus 15x plus 18, y square is equal to x cube minus 3x plus 3, y square is equal to x cube minus 6x plus 5. I have denoted these three equations with three different colors, and I am giving you graphs of these three equations with the same corresponding colors. So green graph corresponds to green equation, the red colored graph corresponds to red elliptic curve, and this violet color leads to the violet colored equation. Okay, all the three are now shown in this following figure. You can see this. So these are the graphs of those three elliptic curves. What are they? They are these. This, you look at this one. Green one, x cube minus 15x plus 18. That green curve happens to be a collection of two pieces. This piece together with this, right? And remember, it is not an ellipse. It is not an ellipse, right? It's not a conic. If you look at a red colored graph, x cube minus 3x plus 3, you can check those conditions. 4a cube plus 27b square not equal to 0, you can check that with each of them. So and hence they are elliptic curves. If you look at the red colored equation y square is equal to x cube minus 3x plus 3, it is only single piece is there. It is single piece, right? But when you look into this violet colored one, y square is equal to x cube minus 6x plus 5, I think this is again two pieces. This one along with this piece. So you can notice that none of these three curves represents any ellipse. So even though name goes by elliptic curves, their geometrical configuration is not an ellipse. Okay, even it is not an equation also, not Not an equation, not a curve. Okay. Let us not worry about that. The name looks misleading. Nothing to worry. Now I want to define addition of 2 points taken from E. And this is the definition I want to impose. It's a typical definition one has to see. What is it I'm doing? Let's try to look at this. Let's try to look at this. Right. Let's start with 2 points P and Q in an elliptical E. You draw a line L through P and Q. Because that is a third degree equation, this line L should meet the curve E in 3 points. Because there are already 2 points P and Q on E, so in addition to these 2 points, there should come another point extra when you intersect this L with E. Take any 2 points P and Q from E and take the line L passing through P and Q. It's going to meet the curve in 3 points because the curve happens to be a cubic curve, right? So it should meet in 3 points. When that meets in 3 points, and 2 points are already known to us, namely P and Q, if there should be some other point extra, namely R. Some other point extra, namely R. Right? Then what I do is, you get that extra point R in addition to this P and Q, and reflect this particular point A comma B in the x-axis, so that the AB's reflection will be A comma minus B. There will be a sign change in the y coordinate. If that point R happens to be A comma B, you take its reflection in the x-axis or real axis, so that its reflection is going to be A comma minus B. This R prime is called the sum of the points P and Q. So that P plus Q is defined to be this R prime, and we denote this R prime by P plus Q. And immediately there are several questions. It's not a ordinary definition, which looks ordinary by appearance. Geometrically, it looks all right. But immediately there come to my mind so many questions. Question 1 is this. How to define P plus P for a point P on E? If I take a point P from E, I should be in a position to define P plus P also. How to define this? So when you are drawing the line L through P and Q, then you have to draw a line through P and P. Line drawing from P and P is nothing but tangent at P. As Q approaches P, then you will be drawing line from P to P. That's nothing but tangent at P. So what to do then? In case that L is going to become a tangent to E at P, and that L must intersect E in 2 points, P and another extra point R. Take this point R's reflection, and that is going to stand for the P plus P. I think this is not going to pose any problem, right? I think this window is visible on my screen share. Is it disturbing you? Hello? Hello? Suresh?
Sir, notice
Sir, it is.
Yeah, this text, is it visible? It's coming
Yes, sir.
the way of this. How to
Several questions arise from this definition. That is what.
But this window is obstructing my text now. Can you
Sir, visible, sir. నేను రాజారెడ్డిని మాట్లాడుతున్నా.
And the point ఏంటంటే ఇక్కడ this particular, it's obstructing my face, and this text is obstructing my text. Can you adjust that one? So can you side that one? Okay, no problem. Is it visible to you? None.
Yes.
So when P and P, that addition is no problem. Take the tangent at P to E, and let that tangent meet the E at R. Take the reflection R. That R prime is going to stand for P plus P. So even though this looks a problem, it's not a problem. Okay, this is a test. But I have got another problem. Namely, what if P is added to its reflection? How to add P, a point, to its reflection? Right? If P is my point A comma B, P prime A comma minus B would also be a point on the same. You remember? So that particular elliptic curve is y square is equal to x cube plus ax plus b. So with a single x, both y and minus y will do. So therefore, if P A comma B is there on E, A comma minus B will also be there on E. So therefore, we need to address this question also. When P is a point A comma B on E, And P prime would also be a point on that. But how to add P and P prime? That's the question. And we shall try to address this question also. So how to answer this question? You can answer this question pretty easily. What you have to do is, you have to make such a thing. And this is what I would like to say. What you have to do is, you draw a line through P and P prime, right? That's going to be the vertical line x equal to a. Am I right? Because line passing through AB and A comma minus B is nothing but vertical line x is equal to A. Okay? And this vertical line is going to intersect your E again in the 2 points P and P prime only. Right? I think there is no third point of intersection for this. And how to go about that resulting point R and its reflection to go for P plus P prime? That's the question. Right? When you take the line passing through P and P prime, it's going to be a vertical line x equal to E. Then this line is going to meet E in 2 points P and P prime. And there is no third point of intersection of this L with E. But then no R is going to appear there. But how to define that R, which stands for P plus P prime? Again, nothing to worry. What I'm going to do is, I'm going to make some arrangement here to avoid this particular difficulty, which is a difficulty by appearance, it can be removed. So to remove this apparently difficult one, what we do is, we just take an extra point O, a typical point, which we call just O. Assume that this is going to lie on the extreme end of that particular vertical line, right? Assume that this is going to lie at infinite distance on this vertical line. It can only be felt, it cannot be seen, please. And refer that P plus P prime as O. And also assume that this O, which is taken to be something like this, assume that it is going to be there on every vertical line, not only on x equal to A. And take that O as sign for P plus P prime. So when we add P to P prime, and the addition is to be taken as O, this is our arrangement I'm making. And it's going to make our discussion smooth and nothing danger is going to come out of this. And in fact, it's going to act something like 0, which is there in the real number system and the addition. Okay, so having done this particular agreement, now another question comes in. How to add a point P to O? And this question we have to address. How to address this question? Then what you have to do is, you have to draw a line through P and O. Is it going to be a vertical line through P? Tell me. Yes, it is a vertical line through P. And it's going to meet that E in 3 points, namely P, O, and P prime. P, O, and P prime. It's going to meet at 3 points, P, O, and P prime. So in other words, this particular line L is going to meet P, O, and R. R here is P prime. So P prime here is A comma minus B. So its reflection is to stand for P plus O then, right? As per the first definition. So in other words, P plus O should be the reflection of P prime. Reflection of P prime. Reflection of P prime. Reflection P prime. Okay. That's nothing but A comma minus of minus B, which is A. So therefore, when P is added to O, it's going to result in P only. I think this is going to agree, which is with the what we are trying to expect. Okay. No problem. This arrangement is going to be all right. When you take the line passing through P and O, it's going to meet that curve E at other point P prime. The P prime's reflection is again P only. So therefore, P plus O is P only. So even third difficulty is also indeed not a difficulty, which appears something like a difficulty for us. And I shall try to illustrate all this geometrically. So when we look into this elliptical E, I have taken P and Q points here. Draw a line L through P and Q. It's going to cut that elliptical at R. So if you look at this, the axis, x-axis, please. And if you, this is my x-axis, please. And if you take the reflection along this particular real axis, you can see that this is R prime. So this R prime is going to stand for P plus Q. That's what I was telling in the definition, right? So what you have to do, take the line passing through P and Q and let that intersect the elliptical E in the point R, take its reflection in the real axis in the R prime. This R prime is going to stand for P plus Q. And when P and Q coincide, suppose Q approaches P, this is going to become a tangent. Then the figure would be something like this, right? Then what to do? You take the tangent at P and let that particular line intersect the elliptic curve at R. And then take its reflection R prime. This is going to stand for P plus P. We also denote this P plus P by 2P. But we also denote P plus P by 2P. This 2P is R prime. I think this is also no difficulty for us. When P and Q coincide, this L is going to become tangent to the curve E at P. Right? So what if your P and P prime ought to be added? This is what you ought to do. So if this P and P prime ought to be added, then you have to take the line passing through P and P prime. It's not going to intersect this elliptic curve at no other point. And what I'm assuming is on this particular vertical line, you are assuming that at some infinite distance, some point O is there. This is a typical point which are just feeling its presence, not its. We will not be in a position to expect that. This can only be felt. It cannot be exhibited. Assume that it's there on the extreme top of this line L. You assume that number to be that particular point to be O, and also assume that this O is there on every vertical line, not only on this. It may be lying on this vertical line. It may be lying on this vertical line. So assume that it is there on each and every such line, not only on this. So with this arrangement, I think our discussion is going to become very smooth, and it's not going to disturb our discussion. So nothing to worry when I do something like this. And this is going to act something like 0, which is there in the real number system under addition. Having done this, and we shall denote the reflection of P in the real axis as minus P, and we denote this one by minus P. So, and P minus P is defined to be P added to minus Q. And similarly, we denote P plus n times as NP. There's small notations I'm making use. And having done this, we shall try to look at one example. What difficulty is involved in adding 2 points on an elliptic curve? Remember, this type of addition of points on elliptic curves is going to be the heart of the total elliptic curve cryptography that we are going to introduce, the time permits. So unless you are familiar with this addition thoroughly, you cannot understand the philosophy behind this elliptic curve cryptography. We shall try to exemplify the same. So take the elliptic curve y square is equal to x cube minus 15x plus 18, which we have seen in the previous graph. Let's take 2 points P7, 16 and Q1, 2. You can verify that these two are there on this. And in fact, it's an elliptic curve. You can see that A is equal to minus 15, B is equal to 18. 4AQ plus 27 B square, you can see that it's not equal to 0, and all those things are there. So we shall first of all find the line passing through P and Q, which is this. You can find it out very easily by using the 2-point formula for the line. So the line becomes y is equal to 7 by 3x minus 1 by 3. It's a simple job one can do with the knowledge of coordinate geometry from the intermediate level. And we should try to find out the point of intersection of this 1 with 2. So let us intersect this, make intersection of this L with the E to find out the point R. So what is it you have to do? You have to solve these two equations for 2 points. So solving these two, we get that 7 by 3x minus 1 by 2 whole square is equal to x cube minus 15x plus 18. After simplification, this is going to result in this one. Again, you may be wondering how to solve this cubic equation. Quadratic, it's okay. But how to solve this quadratic cubic equation? Nothing to worry. We already noticed that when you draw the line through P and Q, and we get the 3 points of intersection of L with E generally. But out of those 3 points, 2 points are P and Q. And these 2 points P and Q's x coordinates are going to be 2 roots for this equation. Spoken differently, if P is x1, y1, Q is x2, y2, that x1, x2 are going to be roots for this equation on. So therefore, even though this looks like by appearance as a cubic equation, its 2 roots will always be known to us, namely in the form of x1, x2, which are x coordinates of P and Q's. So put them back into this one, you can get the third root very easily. So therefore, that's what I've written here. Solving a cubic is difficult in general, but in this particular case, the x coordinates of P and Q are 2 roots of this equation. So they are already known to us to be 7 and 1. So 7 and 1 are roots of this equation. Third root can be found very easily. How to find that? You take x minus 7 and x minus 1, divide with x minus 7 to x minus 1, that cubic equation. You can get that x plus 23 by 9 is another factor. So that third coordinate is going to become minus 23 by 9. If x is equal to minus 23 by 9, its corresponding y coordinate is going to become 170 by 27. You just simplify. Simple calculations are required here. You do this. And so that your point R becomes now, x coordinate is minus 23 by 9, y coordinate is 170 by 27. What about its reflection in the x-axis? Y coordinate gets a change in sign, that is minus 170 by 27. So that's what is P plus Q now? It is R prime, which is minus 23 by 9, minus 170 by 27, right? Similarly, to find P plus P, you have to find tangent to E at P, and you have to find out the R, take its reflection, that's going to stand for P plus P. Here also same thing needs to be done. So for that, what I do is I take help from the calculus to find the slope of the tangent L at the point this P. So slope of the tangent, if I differentiate, 2y divided by dx is equal to 3x square minus 15. So that m is equal to slope of L becomes 3x square minus 15 by 2y. At the point P 7, 16, this becomes 33 by 8. You just simplify to get this. I have verified it is solved. Now you can find the equation of the line L. How much is the equation of the line L? It's y minus 16 is equal to 33 by 8 into x minus 7, right? After simplification, this becomes y is equal to 33 by 8, x minus 101 by 8. We call this equation as fourth one. Now we shall find the points of intersection of this L with E. So for that, you have to solve both 1 and E. So in the place of y, you put this expression into equation 1. So that this is what is going to result in. And after simplification, remember that when you solve this cubic equation, two roots are x coordinates of the point P repeated twice. That's the x minus 7 whole square is going to come as a factor for this total cubic that you get here. Another linear factor is going to become x minus 190 by 64. You can do this. So the third point's x coordinate is going to become 193 by 64. With this x, you can find out your y to be minus 223 by 512. So that the point R becomes now 193 by 64 minus 2 to 3 by 5 and 2, and its reflection x-axis is going to be this one. So your P plus P becomes such a number, right? There are some problems. If I go to another equation, something like this, you can see similar things. Similar calculations are required. Now I got so many problems with this. I have to point it out. So you can just go to these numbers. I have solved them. I will supply these notes to you, right? Now equation comes in. Suppose if I give you an elliptical with bigger a and b's and coordinates with bigger numbers. Suppose in the place of this elliptical, if I give a curve with bigger numbers in the place of a and b's, and if I take the points with very big numbers, finding P plus Q, is there any way out? That is the question. I think unless there is a definite formula for that, finding this one is not that easy, right? I think there is a typical algorithm which goes by the name addition algorithm for the addition of points on an elliptic curve. That is nothing but when we give a formula to find out P plus Q, with P and Q is given to be 2 points on an elliptical E. So we try to look at that particular addition algorithm, which is going to make this job a bit easy. I shall try to look into that addition algorithm to find out some 2 points. So we shall try to look at this elliptical addition algorithm. What does this say? This is going to give you a method of finding P plus Q, of course. This thing, of course, this is going to satisfy all these conditions. I'm not worried about that. I want to look into the algorithm, which is going to give you a formula for addition of 2 points in this. Suppose E is an elliptical, y square is equal to x cube plus ax plus b, and P1, P2 are 2 points on E. Then how to find P1 plus P2? And this elliptical addition algorithm is going to give a precise formula to compute that P1 plus P2. So, which is spoken in this particular formula. And this is going to give you the various cases in which you can compute P1 plus P2, right? So this is the summary. So if your P1 is O, we know that P1 plus P2 is O plus P2 should be equal to P2 as was seen earlier. If your P2 is O, this P1 plus 2 become P1. So nothing surprising. So let's suppose for that matter P1 is equal to X1 and P2 is X2, Y2. If X1 and X2 are same and Y1 is minus Y2, and then P1 is the reflection of P2 or P2 is the reflection of P1. In that case, P1 plus P2 is going to become O. I think there is nothing trouble in that. The trouble happens only when P1, P2 are different points, and P1 plus P2 happens to be some X3, Y3. Then to give a precise formula for this X3, Y3, how to go about this? That is a question. So here we have got a formula. So if one of them is a reflection of the other, there is no problem. Sum is going to be the point O. So none of them is a reflection of the other, then problem arises. But then there is a formula for this also, namely P1 plus P2. P1 plus P2 is equal to, this P1 plus P2 is equal to, say, X3, Y3. Then I'm giving you a formula for X3, Y3 as something like this. Your X3 is lambda square minus X1 minus X2. Y3 is lambda times X1 minus X2 minus Y1, where this lambda is given by 2-piece formula, something like this. If P1 and P2 are different points, then of course with X1 not equal to X2, then lambda is Y2 minus Y1 by X2 minus Y. It's nothing but slope. And P1 is equal to P2, then it's 3x1 square plus a by 2y1. You can even notice that this is also going to be the slope of the tangent line L at the point P1. At the point P1, that's what you can notice. So this is going to give you a precise formula for P1 plus P2. P1 plus P2 here, the time circle plus only. I think this is not a big thing. You can even check this. This proof can be had very easily. When P1 not equal to P2, and there arise two cases. In the third one, P1 may be different from P2 or P1 may be equal to P2. First, we handle the case P1 not equal to P2. So then that particular line L would be equal to how much? Y minus Y1 is equal to M into X minus X1, where M is slope of the line L, which is going to be so much. If I take this one as lambda, we have got this L is equal to Y minus Y1 is equal to lambda times X minus X1, or Y is equal to lambda times X minus X1 plus Y1. So in order to get that reflected point R, you have to solve this particular 2 with 1. For that, let me make some shorthand notation. I can write this Y as lambda X plus V, where V is going to stand for this one. So allow this L to intersect E to get another point R. To get the point R, you have to solve that this equation. I have these details you can see line by line. I don't want to explain them. When I supply these notes to you, you can just go through them. So that when you arrive at the cubic equation, when they put that L into that equation E, you get a cubic to be something like lambda minus X1, lambda minus X2, lambda minus X3, right? So, but then this 3 and this 4 are going to be identical, so that you can compare lambdas, so that you can get X3 is going to become so much. When X is so much, correspondingly R is going to become X3, some Y0, let us say. And if I take this as Y0, and R prime is going to become X3 comma minus Y0. So this minus Y0 is same as Y3, which is mentioned in the sum, P1 plus P2 in the statement. So this Y3 is going to become minus Y0. So putting X3 into the equation, you can get Y0 into the equation of L, put X3, you get Y0, and take negative of that Y0 to stand for Y3. Then that is going to give you your typical third point, that R prime, which stands for that. In the case 2, when P1 is P2, it's going to become a tangent. Tangent slope is this one, which is mentioned there in the second bit of that formula for lambda. So once this lambda is revealed, you can go to X3 by 2 be so much, right? This is what we get. This is known with the name addition algorithm. Okay, having got this addition algorithm, which makes our job easy to find out the sum of points. Yeah, then comes another. Let's try to look at some graphs of these curves. I have made use GeoGebra to find out the graphs of these. I give you some examples of these elliptic curves. Y square is equal to x cube minus 7x plus 3. Y square is equal to x cube minus 7x plus 9, x cube minus 7x minus 12, etc. So these are shown with respective colors there in the graph, in the single graph. Let us leave over this. Now, still there is a problem. With this, the problems are not over. What is that you could see? Finding sum of points on this elliptic curves has become to some extent easy by using a elliptic curve addition algorithm. But if I take the points on the elliptic curve with the bigger coordinates, large coordinates, and with, of course, in the elliptic curve equation, a and b is to be very large, but still computation of these things become very tough. Not only tough, added to that, in the elliptic curve cryptography, what we use is, we are not just going to use ordinary numbers. We are going to use numbers from typical fields. I'm going to take some typical field. Don't worry about these fields where P is a prime. What is this P? P is a prime number. I'm going to take this at 1, 2, 3 up to P minus 1. And I want to impose two operations, namely addition modulo P and the multiplication modulo P. Under this operation, you can verify that. Addition modulo P and multiplication modulo P. These are going to give you the properties that are there with, if you look at this FP under this particular addition modulo P, multiplication modulo P, this is going to enjoy same set of properties which are enjoyed by real number system under addition and multiplication. Whatever the properties are enjoyed by this system, same properties are going to be enjoyed by this system also. So such a system is called a field. Don't worry about this definition. It's purely mathematical in nature. Now what we do is, for the elliptic curve cryptography, we choose elliptic curves, namely y square is equal to x cube plus ax plus b, where a and b's are to come from this particular fp. That is the beauty. Of course, in addition to satisfying for a cube plus 27b square not equal to 0. So what we do is, such a typical elliptic curve, namely such y square is equal to x cube plus ax plus b. We take this typical, this one, over where a and b are to come from this fp, which we call elliptical over the finite field fp. And over such fields, I would like to consider elliptic curves rather than considering elliptic curves over R. In the previous instances, we have taken a and b's to be integers coming from R. Now that I'm going to take these a and b's to come from this set only. When I take points on this curve, this point sort, if I take any point x comma y, belongs to this EB. Remember, this x and y are to come from this particular FP only. So such points only will be considered to be there on this EP. So precisely when I consider an elliptic curve over FP, a particular elliptic curve may contain very less number of points because of these restrictions, may be containing more number of points. It all depends on this nature of the prime number taken. That will be revealed. Don't worry about these discussions, because I'm just taking, you take them lightly, but just listen. When the prime, it all depends on the prime P chosen. With some primes P, there may be more number of points x comma y that satisfy this particular EP. With some primes P, there may be very less number of points x comma y belonging to this EP. It all depends on the prime P chosen. Now our next job is to choose elliptic curves over these finite fields. When I look into elliptic curves over such finite fields, How about these additions and multiplications with the numbers in this, and how to add points belonging to EP over this FP? That's a big question, which we shall now try to discuss. This elliptic curves over finite fields. This is very another interesting way. Our cryptography is going to take place only on with respect to such elliptic curves over finite fields, not on a real field. Okay, we will be dealing with such finite field FPs over which our curves will be taken. That's what I have written here. If you look at this one, an elliptic curve over a finite field FP, we mean it's of the form y square is equal to x cube plus ax plus b, with the a and b is coming from FP, as I was telling. 4a cube plus 27b square not equal to 0. So meeting this requirement, of course, in addition with that point O has to be taken. I have to take that O also into account. So therefore, the points on A ought to be chosen so that its coordinates ought to come from this particular set only. They should not go beyond this. That is the big restriction which is going to be put on this particular points of E. Not every pair x and y such that this one ought to be taken. Only those xy's which ought to come from this one and satisfy this one ought to be chosen into E. So that is my elliptic curve here. Okay. And we denote that one by E over AP or E suffix P, doesn't matter. So we call that to be elliptic curve over AP. It is the collection of points x comma y, where x and y's come from FP, such that this x and y satisfy y square is equal to x cube plus h plus b. Of course, together with that extra point O, which is missing there, of course. So now, surprising thing is that when we take the case considering p is equal to 2, this discussion of elliptic curves over this E over F2 is going to be very, very complicated, and it's going to be beyond your this one. I cannot say that scope of this particular discussion. It's going to be beyond the scope of this discussion. Scope of the discussion. It is very tough, in fact. So what we do is we confine only to this one. Only p greater than or equal to 3. Even when p greater than or equal to 3, now addition and multiplications are going to lead to, or addition of points going to lead to several complications. The complicated computations are to be done when you deal with addition of points, right? Let's take one example. Take y square is equal to x cube plus 3x plus 8 over f13. My prime number here is 13. When I take f to be 13, what are the members belong to this f13 field? F13 0, 1 through up to 12. Addition modulo 13, multiplication modulo 13. 14 means here 1, 15 means 2, etc. So let us now see how many points are there in this elliptic curve E over F13. We shall try to discuss how many points lie in this elliptic curve E over F13, and unlike in the previous situations where we have taken any pair externally satisfy E is a point of E. But now that it's not the case, the point to be there in E over F13, the coordinates are to come from F13. That's what you have to keep in your mind. So if I choose xy to be from E over F13, immediately is that these are to come from F13. Let us enumerate how many points are there in E over F13 with x coordinate 0. If x coordinate is to be 0, by the elliptical equation, my y square should be how much? 8, because x is taken to be 0. So we have to solve this particular equation in F13 to have points with x coordinate 0, right? Let us see. So to get a point with the y coordinate something and x coordinate 0, and this y should satisfy y square equal to 18. How many elements of this particular F13 are going to satisfy this y square equal to 18? We should investigate. 0 square is 8, not equal to 8. 1 square is 1, not equal to 8. 2 square is 4, not equal to 8. 3 square is 9, not equal to 8. 4 square is 16. 16 modulo 13 is 3. 3 is not equal to 8. 5 square is 25. 25 means 12. Modulo 13 I am taking. Modulo 13 means remainder when divided by 13 you have to take. That's 12. 12 is not equal to 8. Similarly 6 square, which is not equal to 8. Similarly you can check that no element among these, any of these, you take any element of this, it is not going to satisfy this one. So what is the meaning of that? You cannot find any points in this elliptic curve with the x coordinate being equal to 0. So in other words, you cannot expect any points in E over F3 with x coordinate being equal to 0. So you can just drop those points with x coordinate 0. We should investigate, are there any points with x coordinate equal to 1? When x coordinate is equal to 1, then y square is equal to x cube plus 3x plus 8. So that this is going to become how much? 1 plus 3 plus 8, which is 12. This 12 is nothing but 5 square. 5 square is 25, no? 25 means 12. So y square equal to 5 square means this is also 8 square. 8 square is 64. 64 congruent to 13 is nothing but minus 1, that's 12. You can see. So therefore, with x coordinate 1, there are 2 points, 1 comma 5, 1 comma 8, right? So with x coordinate 1, there are 2 points, 1 comma 5 and 1 comma. You can verify this, nothing to worry. 5 square is 25, 25 is congruent to 12 modulo 13. 8 square is 64, 64 is congruent to 12 modulo 13, you can check, that's all. And with no other points, this is going to happen. With no other points, this is going to happen, right? So therefore, with x coordinate 1, there are only 2 points, 1 comma 5, 1 comma 8. So therefore, x is equal to 2, check. These are only 2 points which are going to come into picture. With x coordinate 1, 2 points are there. With coordinates x coordinate 2, 2 points are there. Similarly, you just go on investigating. So with x coordinates 2, there are 2 points. With the x coordinate 3, there are no points, you can see. With 4, 5, 6, 7, 8, you cannot see any points. But with x coordinate 9, there are 2 points. With x coordinate 12, you can see 2 points. Totally, how many points are coming into this E over F13? 1, 2, 3, 4, 5, 6, 7, 8, 9. Just 9 elements are there, no more. So therefore, if you consider the elliptic curve, namely y square is equal to x cube plus 3x plus 8 over F13, you just have only 9 points. You just have only 9 points. You may be guessing that there are 13 into 13 points. Not many points are there, only 9 points figure into this F over 13. Similarly, if you look into another example, even if you look into this one, remember listing out all elements of U over F3 or U over FP for any prime given. It's not that is there is no definite thumb rule to find out all the elements of that straight away, but you need to compute like this only. That itself is a laborious job, you can see. So that needs lots of computations here, right? Now we shall see another important example. So let's take E is equal to y square is equal to x cube plus 8 plus same example I'm taking. Let's take 2 points 9, 7, 1, 8 in E over F13. And we shall find what if this, in order to find P plus Q, what labor is to be computed, we shall now see. So again, you make use the same formula. P is equal to 9, 7, Q is equal to 1, 8. Slope becomes, wait. Let me come back to the discussion. So let's take 2 points P 9, 7, 1, 8 in this elliptical E is equal to y square is equal to x cube plus 3x plus 8. Now let's see what difficulty is involved in these computations. So as was by using that addition algorithm, this lambda is going to stand for the slope of the line passing through P and Q, even in this case also, which is y2 minus 9 by x2 minus x1. So 8 minus 7 by 1 minus 9, which is 1 into minus 8 inverse. It's minus 8 inverse, not ordinary decimal inverse, please. It is the inverse in F13. That's what you have to keep in your mind. Okay. This minus 18 inverse, it is the inverse in that F13. So that is, you have to look for, but minus 8 is congruent to 5 modulo 13. So it is 1 into 5 inverse. Remember, minus 18 in the modulo 13 language, it is 5. So 5 inverse. Its 5 inverse is not just 1 by 5 place. Inverse of 5 in F13. Inverse of 5 in F13 is that number which when multiplied by 5 should leave 1 modulo 13. So I think this is going to come with 8. 8 into 5 is 40. 40 is congruent to 1 modulo 13, you can see, right? So therefore 5 inverse is going to become 8 and inverse of 8 is going to become 5, you can see. So therefore this is 1 into 8, this becomes 8. So even though by appearance it looks as if 1 by minus 8, this 1 by minus 8 is nothing but 8. That's what you have to remember. This minus 1 by 8 is not ordinary 1 by 8. It is 1 times inverse of minus 8 in the field F13. So you have to keep your mind in that particular F13 only, you should not go beyond that. Okay, it is not ordinary decimal computations, please. Now we shall compute the line L. Line L is going to become y minus 7 is equal to this. So it's 8x minus 72 plus 7. It's 8x minus 65. Minus 65 is congruent to 0 modulo 13. Therefore, this is 0 only. It is just 8x, right? So the line becomes now y is equal to 8x. It is not ordinary equation in the decimal form, please. It is considered to be there in F13. So therefore, you have to always be cautious while taking these numbers. Because this is congruent to 0 modulo 13, I have taken this one to be 0. So it's y is equal to 8x. Now we shall try to compute this p plus q. So this p plus q is going to become, if I suppose this one to be x3, y3. If you look back into the formula, x is lambda minus x1 minus x2. X is something like this, right? So what is that x3? If you look into the previous formula, it is lambda minus x1 minus x2. And the x3, lambda here is 8. 8 square minus 9 minus 1, which is nothing but 64 minus 10, 54. But 54 is congruent to 2 modulo 13. So therefore x3 is going to become 2. So this number 54 cannot be taken as it is. It is to taken congruent to 13 modulo. Okay, so which is 2. Similarly, y3 becomes lambda times x1 minus x3 minus y1, which is going to become 49. 49 is congruent to 10 modulo 13. So therefore, this y3 is going to become 10. So thus your p plus q is 9 comma 7 is equal to 1 comma 8, which is 2 comma 10. It is not that 10 comma 15. In the ordinary decimal language, 9 comma 7 plus 1 comma 8 is something like how much? 10 comma 15. It is not that here. It is 2 comma 10. Nothing surprising because we are there in the field F13. That's what you have to keep in your mind always, right? So now let's try to compute this p plus p. If you take this p plus p, say take p to be 9 comma 7, x1 comma y1, p and q are same, and compute this one. This becomes how much? 9 square into 3 plus 3, 246 into 14 inverse. Remember, 14 is congruent to 1 modulo 13. Therefore, 14 is nothing but 1. So 1 inverse is 1 only. 246. 246 is congruent to 1 modulo 13. Therefore, lambda becomes 1. So we are always there with modulo 13, please remember. So line becomes y minus 7 is equal to 1 into x minus 9. So this y is going to become x minus 2 ultimately if you simplify this. Lambda is 1. You can find out this p plus p by same formula which was there in the addition algorithm. So this is the complication, set of complications involved in computations in ellipticals with the points in that. Then what we do is in the elliptical cryptography, we choose points P and Q. In this elliptical cryptography, go through all these things. I have done some problems here. You can go through them leisurely one by one, which are going to illustrate the complexity involved in addition of points, taking multiples of points, and so on and so forth. Now I want to pose a big problem with regard to this. I'm going to supply these notes to you, don't worry. Now the problem is this. Suppose if I were to, suppose P and Q are taken to be 2 points taken from an elliptic curve over some Fp, where P is a large prime. Then I want to look into, these are 2 given points, please. These are 2 points given, P and Q. And how to find out this n so that np is equal to q. To find this, to find n such that np is equal to q is called elliptic curve discrete logarithmic problem. Elliptic curve discrete logarithmic problem. In this, what we do is, if I take p to be x1 comma y1 and q to be the point x2 comma y2, what we do is solving this equation for n, finding out this particular n, finding out n, satisfying np is equal to q is called a discrete logarithmic problem in the elliptic curve cryptography, ECDLP. This problem is called elliptic curve discrete logarithmic problem, and this n is called, in fact, discrete logarithm of q to the base p. This is called, in fact, elliptic discrete logarithm of q with respect to with the base p. To find this n with the given p and q is a tough job. This ECDLP is, in fact, a very, very tough problem. When I choose my points p and q in such a fashion that this x1, x2, and this prime x1, comma, x2, and p are very large, then finding n, these are very large, and this finding n becomes very tough. Very tough in the sense, by using the toughest and the powerful algorithms available till today in computing these addition of points on elliptic curves, this finding n is going to be very, very tough job. So based on this particular thing, if you look into some certifications in HTTPS, you can find some ECC, ECDSA. Something appears like this, wherein you will be mentioned with 2. And those 2 are nothing but these x1, x2s will be mentioned there, and p will also be there with underlying. These things will be made public, and finding this n will be tough. And this is going to make the whole job so secret in the elliptical cryptography DLP problem. And even you can look into this elliptical cryptography's counterparts, something like Elgamal's public key and Diffie-Hellman key exchange problems. Their replicas can be seen in this EC. Those problems are going to become very, very tough with respect to this elliptic curves. When elliptic curves are considered over these finite fields where p's are big and the corresponding x1, x2s are big. Based on this particular philosophy, this elliptic cryptography becomes very, very tough. And point is that when you compare this one with the RSA with the usual integers, the length of keys would be smaller, and decryption business becomes very, very tough compared to this RSA. That particular topic is quite lengthy to discuss. I think it is an appropriate place to stop here. And I can stop my lecture here because the time given to me is almost over. Ram, can I stop here?
Yeah, thank you, sir.
Look at some questions.
Yeah, actually, one question. I can't say it's a question related to this, but in general, do we have any jobs based on cryptography, sir? This is from Vidyasagar.
Repeat once.
Do we have any jobs based on cryptography?
Oh, I remember. Okay, that's a good question. In fact, everybody has to listen to this. If you look at the present day scenario, there is a large demand, very big demand for 3 kinds of people, namely data analysts. Okay. Second one, in the coding. Third one, in cryptography. These are the 3 areas where the right people are not there. There is a very big scope for the people to enter into this particular cryptography, and huge amounts are being paid to the people who are working in this cryptography and coding theory. Coding theory is one who is very familiar with various languages, and that fellow can code the problems. But cryptography is very powerful area and a very on demand. In fact, it can embed n number of people because the right persons in the cryptography are not available. One who is familiar with the number theory and algebra are on great demand. Even one who is familiar with algebra and number theory, and they are on great demand in this particular cryptography. There is a large scope, not only job, large scope. They will be highly paid. Ordinary jobs are not available. Certainly, jobs of a high reputation are available, and they are paying very high. They are being paid very high compared to ordinary jobs in the computer science. So there is a large gap for the people to work on this data analysis. It requires a lot of knowledge in various computer languages, and the coding also requires knowledge in computer languages. Cryptography is something beyond all this. So there is a larger scope, very, very big demand for the people working on cryptography.
Fine, sir. Thank you. There is another question from Narasimha Raju. Can we take a different finite field in place of FP?
Yeah, any field, any finite field will do. The security lies on choosing that particular FP where P is very large. Large in the sense, it should be a prime consisting at least 200 to 300 digits. That is the point I'm talking about. Raju, I think he may be listening to me. I'm talking about the primes here, not large in sense and having hundreds of digits. People are working with hundreds of digits, right? And we are taking finite fields with P being so large. And from that, over that, I'm taking ellipticals. And over that elliptical, I'm trying to look for the Telegramm's public key crypto system and Diffie-Hellman key exchange and this RSA. So that is going to make this total job very tough. Any field can be chosen, but if you choose a field with 13, something like 73 or 97, such things are very, very simple and silly. Large in the sense, consisting hundreds of digits, not 10 digits or 15 digits or 20 digits, right? It is that particular prime field which is very large in size, okay?
And another question, sir. Is there any general formula to get order of EFP?
Order of EFP, no, that's what I'm telling you. With some prime space, surprisingly, the number of elements in E over FP is very high. With some primes, it's very low. In fact, I have several examples in my lecture. You can see. Surprisingly, with some prime P's, only just 4 elements appear. In some example, there appear so many primes. So that is also going to add difficulty to this elliptical cryptography. So the nature of number of points in this one itself is very tough. And there is no thumb rule, there is no formula for finding out all the elements of this, or at least the number of elements in this one. There is no formula for that. Number of elements in E over FP, there is no different formula for this. But with some special case of P's, there may be some rough estimates for this. But with more general prime number P, there is no rough estimate for the number of elements in this E over FP. So these are the things which are going to make all that ECC, elliptical cryptography, a tougher one over RSA. There is no definite formula for that. So with some primes it's very small in size, with some primes it's very big.
Okay. Thank you, sir. We have come to the end of this question answer session.
Okay.
Let me go for a vote of thanks for this session. It gives me immense pleasure to deliver the vote of thanks on behalf of participants and organizers. Sir, this session is very informative, and you have started the session by explaining the process of key creation, encryption, and description in RSA public key crypto systems by taking a practical examples even from CBIT website. Sir, you have slowly went to mathematical application part of elliptic curves cryptography and elliptic curve additional algorithms. Sir, you have explained greatly the application of number theory and cryptography. On behalf of Department of Mathematics, I thank you for your wonderful and very useful presentation, sir. Thank you very much. Thank you one and all.
Thank you all for listening to me so patiently and so leisurely. Thank you so much. Thanks once again. Right.
Thank you very much, sir.
Shall I quit?
Thank you. Yes, sir. Thank you. Thank you so much.
Okay.
Now I request Padma Madam to introduce the third session speaker.
Thank you, sir. Am I audible, sir?
Yeah, Madam. Please proceed.
Okay, thank you. Good afternoon, one and all. I'm Dr. Padma Reddy, Assistant Professor of Department of Mathematics, CBIT, here to welcome you all for the third session of this seminar. On behalf of the Department of Mathematics, which is organizing the seminar, I extended my warmest greetings to everyone. And I take the honor of welcoming the speaker, Dr. M. Swamidas Garu. Dr. M. Swamidas Garu, Professor, Department of CSC and Joint Directors, Academics, CBIT. He did his PhD in image processing from JNTU, Hyderabad. Sir has 25 years of teaching and research experience and published more than 20 papers in various national and international journals. Sir audited few courses at CMU, Pittsburgh, USA, presented papers in international conference at Shanghai, China, and contributed in open source technologies and projects. Sir is also member CSC BOS of few institutions and member of various professional organizations, including ISTE, CSI, IETE, Svecha Executive Member and Academic Chapter Convener. Now, ladies and gentlemen, let us now welcome Dr. Swamidas Garu to deliver the lecture. Sir, over to sir.
Thank you,
Welcome,
madam.
sir.
Can you hear me, madam?
Sir, it is not audible that much.
Your voice is not clear, sir.
Now?
Yes, sir.
Is it visible?
Yes, sir.
Yeah, respected organizers and my dear participants, very good afternoon. First of all, I would like to thank the organizers for giving me this opportunity to share some of my thoughts regarding cybersecurity and cryptographic solutions. This is the broad agenda that I am going to give a brief introduction about the cybersecurity and the need of cybersecurity and some of the cryptographic solutions in cybersecurity and the directions towards this. From the morning, you have two lectures that is the base foundation or the basis for cryptographic algorithms. Now coming to this topic, I think in the recent period, everybody is talking about the cyber security, the term cyber security. Even AICT is also included in the emerging areas, and also UGC or AICT are also asking the institutions to make cyber security course as a mandatory course. But why there is so important for the cyber security? There are certain questions. If you go back 2 years back, there were some disputes or the issues where the Facebook owner Zuckerberg has to be there in the Senate to give explanation regarding the Cambridge Analytica issue, where the Facebook is having huge amount of subscribers data. The data was analyzed by the psychology department of Cambridge University, and that data has been used in the elections of last term elections of US, the BR, and some parts of India. And also in the recent period, government of India banned certain 56 applications. Of course, the reason may be different reasons where they want to ban China applications. And finally, they banned with the name of they are violating the data privacy rules. And also, if you see the growth of Geo, Geo is one of the largest telecom service provider, which is having a 38.75 crores of subscribers. It has started its operations in 2017, and in the 3 years period, it has become a almost monopoly. And in spite of due to this corona, several industries or the companies uh, lost their businesses, and in spite of that, Geo could make a breakthrough. It has made huge profits. And in the recent period, video conferencing tools also made use business, especially the Zoom app could do a business of 169% of the profit. Of course, US and India also banned this app. In spite of that, Zoom could do a business. Apart from Zoom, there are other video conferencing tools which are making business huge amount of businesses. Some of the applications are giving these services free, and some of the applications are giving service with a nominal amount. Whatever the amount that they are set up, they are use the amount for setting giving these services are very huge amount. But in spite of that, these companies are able to give the services almost all free or with a nominal fee. Why these companies are giving free? How they are able to make this profit? It is because of the customers' data. And also there are several disputes regarding other project, and the Supreme Court also given the judgments on other project. So the customers privacy is the important. These are the various things. Now for all the companies and industries, the data has become a fuel. Every company or every IT industry is looking for the data. With this data, they are able to make use of profits. If you see some of the statistics, in 2019, first half of 2019, here 4.1 billion records, medical records. Most of the records of the medical records are exposed to the hackers. At the same time, if you see from the reports, there are different reports, survey reports from different companies. For every 39 seconds, there is an attack. There is an attack for a day. There are 2,244 attacks are there as per this report, and 53% of the companies. In general, it is usual practice. Most of the employers will access to the organization's data. According to this survey, 53% of the companies where more than 1,000 files, sensitive files, are accessible for their employees, and also the major organization that lost their business due to this data leakage are the medical approximately according to this 6.5 million dollars the data those companies spend that much of amount. According to the Gartner's report, it is expected that $133 billion are going to be spent by various companies in order to get back their data. So, because the lot of hackers and these people are collecting the data, stealing the data in order to get back the data, so they are paying. And in 2018, most of the attacks are the phishing attacks. 62% of the attacks are phishing attacks, according to Sibling Solutions. And also most of the cyber security attacks are being increasingly constantly 68 when they are interviewed according to the Accenture report, 68% of the business companies are facing this problem, and only 5% of the companies are having the foolproof where they are protecting the data in various aspects. 70 out of these attacks, out of these data breaches, 70% of the data breaches, data theft is for financial purpose. Only 25% is for espionage or the revenge kind of thing. The remaining 4% maybe for the freelance hackers or those people. And out of this, 52% is the data breaches are through hacking, and 28% of data breaches are through malware, and 32%, 32 to 33 are through phishing and social engineering. Social engineering is also another kind of source where the data is being stolen. Now, on an average, generally it is very difficult to identify your data has been stolen by somebody else. So, on an average, according to the IBM survey, so it is a 2,206 days. Once that identified it, there is a data breach. In order to get back the data, it took on an average 314 days. And 500 million customer users data has been stolen by the hackers in 2014, which was published, which was made available in the public domain in 2018. On an average, according to the security intelligence, the data breach cost in 2019 was $3.92 million. At the same time, in the same year, 2016, there was a hack of Yahoo server was a hack where the hackers are collected 3 billion Yahoo accounts. According to this information is according to New York Times. In 2006, in the same year, another 57 million drivers information. That data actually belongs to Uber. The Uber has announced this disclosing of information, but Uber has paid large amount for getting the data or in order to keep the data calm by the hackers. At the same time, as 2017, 412 million user accounts were stolen by the hackers. Whereas here, if you see here in 2007, not only the email customers, not only the companies, not only the individuals, also the hackers try to collect the data belong to consumers. Here, 147.9 million consumers were affected by the data breach attack, and that is costed $4 billion. Here, most of the data leaks or the most of the this data theft is due to malware, and that malware is generally used to 94% of the malware is spread or delivered to the end users in the form of emails or the attachments. In the emails, there may be suspicious links. Whenever you click the suspicious link, a script may be run, and that script may be sending the data. That may be a vehicle for the hackers. And here, the 50% of the business are hacked with a kind of attack is the denial of service attack. And 1,000 here 1 lakh customers or the machines were hacked by one virus in 2007. This is one of the biggest attack in 2017, where it costed $4 billion. And generally, most of this malware or the hackers can enter into our systems by attacking the IoT devices. On an average, for every month, generally there are 5,200 attacks for every month. There are that many attacks are there. Here, the WannaCry is one of the ransom malware. This ransomware could earn $133 million in 2019. So generally, what this virus does is, once this virus enters into our system, it will halt our system, or it will encrypt our data, and this encrypted data it will take back, and it will demand for the money. Once the customer agrees to give money, then they will release the money. They release their data back. In this way, the ransomware could earn $133 million in the last year. In 2018, on an average, 1,573 malicious mobile apps. Nowadays, most of the people are using mobile applications. So in 2018, 10,573 applications were attacked by this malware, according to the semantic report. Which kinds of companies are the organizations affected for these kinds of data theft or the data leak? 43% of the this data leakage is for the small businesses, and also there are financial and manufacturing services. There are healthcare and pharma sector is also there. Biotechnology sector is there. So here, for these companies, healthcare and biotechnology, these are the major departments or the major industries which were affected by the this data leakage. And banking is also there. In 2018, the banking has paid $18.3 million for the hackers. And not only the companies and organizations, the bigger organizations, also there are smaller organizations. These organizations were affected with the malicious files. In especially by coming to the healthcare industry, the malware, the ransom malware, hackers could earn $100 million, especially with the medical data. They could enter into their medical device through their medical devices and could stop the medical services and collect the medical electronic medical records and those things. So here in 2019 itself, according to this Safe at Last survey, $25 billion were lost by the healthcare industry itself. In the recent period, like Flipkart, Amazon, these companies, there is a change of supply chain. Here, the supply chain is also one of the loser for the data hacking. According to this Gartner's report, it is expected that more 50% of their security budget is going to be spent for the security services, and on average, whenever there is a data breach, on average, a company has to pay. It is estimated by the Gartner $3.9 million, and in order to get back a record, if a data there is a data leakage for every record, on an average it is estimated that $150 for every record. In the recent period, when people started Zoom app, the hackers collected because that these apps were given freely, and simply by registering with the Zoom, people could install the Zoom app in their machines. And whenever you install these applications, that it is a vehicle for the hackers. Your data has been collected, and they kept our data in the public domain. So that's why the US government or Indian government banned that. So they told that the cost of each record is $0.05 or something else. Depending upon the cost of the sensitivity of your data, that the cost will be varying. So here, almost 50% of the countries, 50% of the large enterprises are spending at least $1 million or more for that. As just now, Professor Govardhan said, here for the cyber security experts, the payment is very high. Generally, this varies from $250,000 to $290,000. And also there is a huge employment is going to be created. As of now, there is a huge scarcity of the job market. It is estimated, according to the surveys, it is estimated that 3.5 million jobs are going to be created in the area of cyber security, and the pay is also highest when it is compared with the normal computer architect or the computer programmer. From 2015 to 2018, the growth rate is expected. The expected growth rate is 5%, only 5%. Whereas in the cybersecurity field, the growth rate is going to be of 700%. This is the huge demand. As of now, there is zero unemployment unemployment requirement. So in this field of cyber security. Now there are different types of attacks. Phishing attack is the major attack. Generally nowadays the hackers are using very sophisticated tools, artificial intelligence, machine learning tools, where they are sending the suspicious link through the links or through the messages that they are sending. Whenever the customers uses these messages or these clicks these links, the phishing attack starts sending the data to the hacker. Then the second type of attack is the viruses, especially in the recent period. The most powerful virus is the ransomware WannaCry attack. And also this attack is a very powerful attack, and also it is able to succeed because of the services of cryptocurrency, because these cryptocurrency people are providing the services to transfer the money when they have demanded. And the data leakage is another kind of thing. There are several solutions for the data leakages. Generally, we think that our data is now no use for them, but our data is very much useful for them, because with our data only, all these companies are able to make huge profits by sending the targeted advertisements or other things, if not banking and financial transactions. And there is another kind of hacking, crypto hacking, where these malware programs will enter into a genuine network, and it is going to enter into the customer network. Customer network is going to be, the performance is going to be degraded by the crypto jacking attacks. Inside an organization, there may be employees, or there may be employees of different kinds in order to take revenge, or in order to, if they are not paid fairly, or if the employees move from one organization to another organization, still there is a difficulty, still there is a possibility to steal the data. And also some of the states or countries are also sponsoring through various means. Here, if they are the manufacturers of the IoT devices, through the IoT devices they may be sending the malware. Or there are medical devices. In the medical devices nowadays, all the medical devices are software controlled devices. Through that they are sending the malware. And also there are third party vendors. Nowadays most of the people are downloading the apps through different sources like Sourceforge or Apple Google Store or other stores. So these third party softwares are also are being vehicles for the these hackers. And also there are millions of connected devices. So for example, here autonomous vehicles are there, autonomous other devices are there. These are the also vehicles. When in the 2019, where I said the ransomware made $133 million, most of the money that these hackers, ransomware hackers, have collected 77% of that $133 million. They have collected from the Canada, and 22% from Germany, another 42% from UK. But most of the attacks were US. 97% of the US companies denied to pay to hackers, in spite of they have theft their data belonging to so many organizations. Now that is from the kind of hacking or cyber related unethical kind of thing. But there are companies which are doing business with the customers' data in a legal form, in with rules and regulations. Whenever you are installing certain applications in your machines, you may be giving your agreement by selecting that agree term. So it is an end user license agreement. So that end user license agreement is collecting. So even for telephones also, we may be whenever you are making a call to a company, they will ask, this call is recorded for the testing the quality of the service. So in this way they are collecting the data in a illegal manner. That data they are selling to the companies. In that way they are making huge profits. If you see from 2010 to 2019, there are companies, these companies are said to be government companies. One is a Google and Apple, Google, Apple, Facebook, Amazon, Microsoft. If you see the top 10 companies which are there in the top in the market share before 2010, generally you can see some company, only the Microsoft was there where in the top 10 countries, top 10 financial companies. And those companies, most of the companies may be in the power sector or in the banking or insurance. After 2010, there is a change. After 2007, for example, if you see here, the first company is Google. In 2010, Google market capital was $191 billion. Where coming to 2019, there is a 541% of hike is there. And also, if you see the Amazon $60 billion company in 2010, in 2019, it has become a $865 billion. There is a growth of 148%. Here you don't see any companies, which are producing the products, but all these companies are giving digital services, or these companies are providing some service. For example, all of we are using Google is providing us emails. Google is not only providing Google Drive, it is providing 25 GB space. It is providing where you are keeping all of your photos, all of your experiences, your whatever the files that you are sharing, everything you are handing over to the Google. With the data, Google is making huge amount of data. This is one way where your data has been used by the companies in a legal manner. And especially if you see in the corona period, in this quarter 2020 quarter, first quarter, Amazon is able to increase its business 26%. So from $59 billion to $75 billion. Not only this, all these 5 companies are able to increase their businesses, where automobile, healthcare, and other sectors, their businesses have come down. All these companies are able to make businesses their profits because of the data only, either legal form or illegal form. There are other driving forces where there is advancements in the information technology. The hardware device cost has come down drastically. At the same time, IoT-enabled devices have come, where the IoT devices are being used in consumer market, commercial market, industry, military, and infrastructure, IT infrastructure. Especially if you see in 2020, there are $30 billion, $30.73 billion devices, IoT devices are there. All these IoT devices are able to communicate with each and every other. These are the vulnerable points for the cyber hackers. And in order to provide nowadays, without having any device, just with a mobile phone or just with a laptop, you are able to do anything. I think most of you people are listening through mobile phones, where you must have installed Zoom app, or directly maybe using a browser. You are giving access to that Zoom app, zoom.us. That server is collecting your data. Your data has been recorded there. So that is here. This server is being run in the cloud. So all the infrastructure is available in the cloud, which is provided through the networks, where this infrastructure not only runs your applications, they provide you hardware, they provide you the data, they provide you the storage, they will provide you lot of things. All these services you need not have in your machine. You can have these services through the cloud. So these services can be accessed through mails, can be your mobile phones, or client programs, and etc. These are the vulnerable points. And another reason for the increased attacks is for the increase, not only the attacks, at the same time, other way, your people are able to get the services, but they don't know they are being in surveillance, because all these IT companies are investing their money in the form of surveillance capital. They are monitoring you and collecting the data. With this your data, they are making business. Here in North America, 94% of the people are able to are having the internet access, and different regions in the whole world is having internet connectivity. Here, on an average, 69% of the whole world is having the internet connectivity. And also the number of social network users are also increasing year by year. Out of 700 plus crores of people, 343 people are having, according to this survey, this many people are having internet connection and social network, these things. If you see social media of people across the world, 381 crores of people are having social media, the social media users, either Facebook or some other medias. That is approximately, it is a 49% of the world people are the social users, social network users. And especially in this third quarter, there is an increase of 8.7 increase, because due to this corona and other things, the social users subscription is increased by 8%. And out of this 99% of out of this 381 users, 99% of the users are using mobile devices. Mobile devices are more vulnerable to hacking or attacking than the computers. And if you see the statistics of this social media users, Facebook is the number one, which is having around 250 crores of people users, where the WhatsApp is also having 200 crores, and YouTube is also having 200. According to the statistics of API statistics of 2020, there are other social media platforms and those things. So this social media is also one of the vehicle for the attacking, because for this social media, simply you are downloading the application, simply you are using like Share It or whatever it may be, TikTok or whatever the applications you are downloading. When it is downloading the applications, there may be security breaches, software breaches, there may be some hidden code. This hidden code is doing all the stuff that is required for the hackers. Not only that, also the communication technologies are also giving a raise to the hackers. After 2G and 3G, and now people are using for some of the people are in the other countries 5G are using. It is easy for the people to get huge amount of data in a shorter time. Now that is here the ultimate goal of hackers is the data. Of course, in the initial days they may be banking and they focused on banking and other things. Now they are focusing on data. Now because the data is the main fuel. Who will do this hacking and where they will do is the question. Generally, here a survey was conducted in the UK on the universities when the universities are given holidays and from 2017 summer to 2018 summer, they conducted a survey. These are the survey results. According to these survey results, there are attacks. These are the distributed denial attacks. So here, these black spikes are the holidays. During the holidays, there are less number of hacking. During the working days of university, there are more number of hackings. Generally the more number of people will be there in the university during their studies. In the vacation, generally they used to go home or relax. So the hackers, probably the hackers may be the students and staff or the people who are working research at universities. These may be the people who are going to practice the hacking or create that hacking kind of things, especially on the university sites. Generally, what were they generally used to attack the networks and attack the services for fun, for making use of a fun, or just taking the glitch or on somebody else, or because they have the time in order to check the vulnerability of a particular system. Generally, these are the possible reasons. Whereas it is a professional hacker, generally the focus is the 75% of the hackers, professional hackers, focus on financial. If they are the students or the academicians, generally these people will try to hack the systems in order to test their vulnerability, their capabilities, or test the vulnerability of other systems. Now, as from the morning, I think morning you have studied so many. You have studied in the morning two sessions. The speakers have discussed about the foundation number theory and also cryptographic algorithms, because there is a possibility of data leakage, or there is a possibility of destroying your networks, or some of the virus may decrease the performance of your systems, and there are the various things. In order to avoid those things, we need to have a cryptographic system where we can protect our systems from the hackers. For that, so generally there is any cryptographic system. Generally there may be when for example, generally nowadays most of the time we are sending the data from one page to another page. Whenever you have created the data, that will be in the plain form. Before sending, that is to be given to a encryption algorithm. These encryption algorithms, you by using the keys, it will convert the data into cipher in a encrypted format. That ciphertext is transmitted to the other side, and other side, by using the decryption algorithm and the key, it is going to be decrypted. If at all there is a hacker which is spying the network and collecting these packets, in order to decrypt this, he has to put a lot of effort. The effort that a user puts for breaking this hypertext into in order to find the either keys or the plain text, that effort generally we call it as a cryptanalysis. How perfectly we can transform this plain text into ciphertext by making use of this algorithm. So developing these algorithms, art of developing these algorithms is called cryptography. Altogether, you may be calling it as a cryptology. So this is the general principle. There are different reasons for making use of these cryptographic systems. There are six general issues. One is the confidentiality. Whenever I want to send the data to the other side party, I want to send this data in a confidential manner, so that even the attackers capture this information, they should not be able to read my messages. So you need to find algorithms to provide that confidentiality. Whenever I am sending the data from one place to another place, the data should not come from unauthorized party, and my data should not go to an unauthorized users. So ensuring your data is originated from the correct source and is sent to the correct destination is called, generally we call it as a authentication. And whatever the data you are sending from source to destination, this data should not be modified by the intermediate people or the hackers. So the mechanism that we employ for providing this integrity, there are different algorithms are there. And also, whenever I want to provide as I committed, I promised as my customers, I will provide these services all the time. At any cost, I need to provide those services. So my services should not be denied by the customer. So this is the denial of service. In the recent attacks, most of the recent attacks, apart from malware, the DOS attacks, not only the DOS attacks, these attacks are distributed denial of services attacks. And whenever you are providing the services, those services should be available all the time, all the days. So for that, you need to have a fault tolerant kind of system. And whenever you are providing the services for different people, different services you are providing, for example, banking, there are different kinds of transactions, different kinds of people. So those services should be provided in a controlled manner. So all these are the issues. These issues are going to be dealt by the network security or information security. Here, the cyber security, there are different kinds of securities. There are slighter differences are there. So any cryptographic system, these are the 6 components. Your plain data, whatever the data that has been generated by the sender or the machine, this is the plain data, first component. Your encryption algorithm is going to be the second component. Your encryption key is the third component. The ciphertext is the next component, and the ciphertext is to be converted back to the plain text. This is the decryption algorithm, and a key is required. So these are the 6 components of any cryptographic system. So based upon the type of the processing, based upon the number of keys that you are using, this encryption process, these encryption algorithms are 2 types. One is the based upon the processing, how the information is, plain text is processed by your encryption algorithm. One category, how many keys are used, which key is used for what. This is another way. According to the first dimension, the encryption algorithms are divided into, the ciphers are divided into, block ciphers are, and other category is the stream ciphers. In the block ciphers, the data is going to be divided into blocks. For example, if you have a use file, every file is going to be divided, let us say 64 bits, or let us say 512 bits, or 1024 bits, or 2048 bits. Each block, that is called a block. Each block is going to be encrypted, and other side it is going to be decrypted. Rather than dividing the data, processing the data in terms of blocks, each character may be encrypted, and other side it is going to be decrypted. The stream ciphers process each and every character by character, whereas the block ciphers process the data block by block. Based upon the number of keys that you are using, the algorithms are divided into symmetric encryption algorithms or asymmetric encryption algorithm. The same symmetric encryption algorithm is also called private key encryption algorithm. Under the private key encryption algorithms, there are several standard algorithms. The data encryption standard is there, advanced encryption standard is there. Here, IDEA is also there. The Blowfish is there, RC5 is there, uh, uh, etc. At the same time, there are asymmetric encryption algorithms where 2 keys are used. One key may be private key, other key may be a public key. Just now, the Gordons has dealt with these algorithms. These algorithms are public key encryption algorithms. RSA is on standard public key encryption, digital signature for authentication, DP-Hellman key exchange algorithm, LGAML, ECC, and password authentication algorithms. There are different algorithms. These are the different algorithms. Here, coming to the private key encryption algorithm. So one key is used for encryption. This is the plain text. Using the one key, it is encrypted. The same key is used for decryption. So in order to get the plain text. Here, in public key encryption algorithms, 2 keys are there. So generally, the public key is going to be the receiver's private this is the receiver's key. Whenever I want to send the data to this receiver, I will use this key in order to encrypt this data. So every key will have its own private key. Whenever a sender sends a message using the receiver's public key, only the companion private key is available only with the receiver. Only that receiver can decrypt that ciphertext. So here there is another way. Here the sender can send a message by encrypting using his private key. Uh, and this message may be decrypted by this. Only this receiver can decrypt that message. So the sender's private key is used for sending the data in an authenticated manner. The receiver's public key may be used to encrypt this plain text. To encrypt this provides the confidentiality. Here, from the morning, you have been studying mathematics. Here, the RSA is strongly based on the mathematics. There are powers are there, modulo and other things are there. Generally, the public key encryption algorithms are takes a longer time. They are powers. They are powers where the private key encryption algorithms are most of the operation they use is the R operation or shift operation or exclusive or operation, simple Boolean operations they use, and only one key they use. Here, private key encryption algorithms takes lesser time for encryption or decryption process, where the public key encryption algorithms takes longer time because a lot of mathematics is involved here. Generally, we don't use for public key encryption algorithms for providing confidentiality. We only use public key encryption algorithms for exchanging the keys or for generating the keys and those things, whereas the private key encryption algorithms are used for data transmission for providing confidentiality. So these are the cryptographic solutions for confidentiality. There are standard data encryption algorithm. There are variations, double days, triple days, advanced encryption standard, IDEA, blowfish. These are the mathematically proven algorithms. As Sir said, all the algorithms are very foolproof. Based upon these algorithms, there are a lot of security tools which are built up. Here, authentication, the RSA can be used either this digital signature standard, digital certificates for providing authentication. These algorithms can be used for providing confidentiality. Most of the softwares, standard softwares, if you have procured, if you have purchased, generally those softwares are downloaded with a authentication key. That key may be a secured hash algorithm or message digest 5 or message digest 4 or 6 is also there. These algorithms will ensure your data has been transferred from source to destination in a original form. Even attackers are modified, these algorithms are able to detect. And for denial of service, in order to prevent denial of service, there are several solutions. Security services solutions, firewalls. A company can have a firewall. A company can have its own virtual private networks, or in the organization, all the machines may be installed with antivirus or anti-malware or spyware. Why? Because nowadays most of the data leakage is due to malware. So these are the anti-malware, anti-spying softwares are going to prevent from those data breaches. And also there are access control mechanisms, passwords and one-time passwords and others. These are the solutions where you can protect your networks. Now here I want to give some directions. The last question in the previous section, I was there in the previous question. There are questions. What are the opportunities? As I said, in the cyber security domain, for cyber security professionals, there are tools are there based on these mathematical principles. All these tools are built based on the mathematical principles, and these tools are available from standard companies like Juniper, Semantic, Cisco. There are so many vendors are also there. There are no professionals who can make use of these tools. So huge number of jobs are there for the cyber security professionals. These people are not going to create the tools. These people are going to make use of the tools in order to detect there is a security breach are there is a data breach are there is a malware. These are the tools. In order to set up these tools, in order to monitor the networks, there are different roles of jobs are available in the cyber security area. For example, here the forensic analyst, for as SR said, there are a huge number of jobs in the data science. So the security, by making use of the security tools, they can become they can play a forensic analyst role. Or information security officer, there is a security manager. This is one more job, and security administrator is there. Security cyber security analyst is there, cyber security specialist and computer forensic examiner, or vulnerability test. There is a network, whether their network is vulnerable, there is a machine, that machine is vulnerable, or there is an application, whether that application is vulnerable or not. In order to assess the risk and all those things, These are the various kinds of jobs, roles are there. These jobs are going to be created, and all these jobs are very highest paid jobs. In the recently, the government of India also is going with a special mission. They have set up center of excellences in cyber security. In Hyderabad also there is a organization, Data Security Council of India, which is running this Telangana State Cyber Security Center of Excellence. Here, all these Center of Excellence purpose is to prepare the people, to inculcate these cyber security skills with various levels. There are 6 levels with QP1, QP2, QP7. There are different six to seven levels of quality packs. Or their government is also providing lot of funding, giving lot of funding for this center of excellence in order to make skill oriented security professionals. Apart from the skill oriented jobs, there is huge scope for the people, academicians, for the students who are want to go in a research orientation. Still there is a scope. A lot of huge number of open source tools are there. Huge number of open source tools are there. Generally these open source tools are available along with the source code. Here, rather than downloading the applications as it is, executable form, you can download the source code and compile it. You first read that code, and then once you are satisfied there are no security breaches, there are no loopholes in that code, you can compile and you can set up and install on your machine. So that is one way you can create products, security products, downloading the available security products and customize according to your requirements. And also there are open source tools are available. Those tools can be made for your research purpose rather than spending crores of money. And also there are several open source freelance researchers are also there. The lot of open source resources are there, and you can have collaboration with those research scholars, and you can work in a collaborative manner to develop new security tools. And also in the recent period, the deep learning is one of the latest technique where it can learn the knowledge from the huge amount of data and develop models. Based upon those models, you can build the tools. These tools can be made available to the companies and industries. And also the computational power is also is increasing. Now we are having the GPU based computing, so your research can be done. Earlier, it used to take 2 years or 3 years for your computation, verification, all those things. Nowadays, huge amount of computational power is there. Even you can modify your algorithms with a huge numbers, larger size, where the complexity can be created. These are the research opportunities or the job opportunities in the field of cyber security. So there are some differences with the cyber security. There are different terms, confusing terms. Generally, there are network security is there, information security is there, cyber security is there. On top of information security is the highest one, and cyber security is a branch of information security, where network security is a branch for your cyber security. Basically, cyber security is nothing but it is a practice, and all it is a set of techniques and methodologies used to protect the integrity of our networks and devices that are connected to that network, and programs that you are installed, and the data that is there in your system. In order to protect your programs, your data and your applications and your infrastructure, a set of procedures and practices are there. Implementing those procedures and practices is nothing but your cyber security practice. So generally, the cyber security protects the completely all kinds of digital sources that are belonging to an organization, including the applications, where the network security is a restricted one subset of your information, your cyber security, where it focuses of protecting our files within a system or the directories, and also directories that are there in the computer which are connected. And they will try to protect our data, this data, from misuse or hacking or unauthorized access. So the network security professionals will try to protect the infrastructure of this infrastructure, whereas this is a global. And for network security, the people generally use IDs, passwords, internet access, use control, set up the firewalls, and take the backups periodically. Even there is a attack or there is a data theft, even the data theft is done took place. If I have backup, then I can recover in a faster way rather than paying to the attackers. If there is a sensitive data, you have to get back the data. So these encryption algorithms and all these things, this is under network security. Um, and other one is the cyber security. So most of the years, the recent period, if you see, especially in the academic domain, most of the colleges are going to start new courses. Universities are starting new courses, cyber security courses, and also the cyber security course is taught to all the people. So in order to uh, create these professionals, there is a use scope. Even the colleges also, there are opportunities for us to teach these foundations, and in order to create new tools or in order to strengthen the existing algorithms mechanisms. Still there is a scope for the mathematicians and computers combinedly. If mathematicians and computer science people work together, so there is a possibility and opportunity to create new tools in order to protect all these things. Definitely it is going to play, cybersecurity is going to play a major role in the industry as well as the country's GDP. Also the lot of things are also there. This is what I wanted to share with you people. Now it is over to the organizers. If any queries are there.
Thank you, sir. But there are no questions, sir.
Okay.
Thank you, sir, for the wonderful session. Now let me go for vote of thanks.
Swamidas sir.
Sir.
Hello.
Swamidas sir, stay back, sir, stay back.
Yes, yes, sir.
Hello.
Madam.
Okay, sir. Let me go for vote of thanks.
Okay, madam.
We are honored and delighted with your presence, sir. I take this opportunity to thank the speaker of today's third session, Professor Swamidas sir, for the valuable inputs. Sir, your in-depth knowledge of need of cybersecurity and facts, cryptographic solutions for cybersecurity, and how to evaluate cybersecurity problems, and opportunities and future directions in the field of cybersecurities, and your ability to present the subject in such an interesting way created an excellent platform of learning and made this day memorable, sir. Thank you, sir, for stimulating the lecture. Thank you so much. Now, I request Dr. Sharada Madam to give a close ceremony and vote of thanks. Over to Sharada.
Good evening. Am I audible, sir?
Yes, Sharada.
Yes, madam.
I request Professor M. Swamidas Garu to chair the next session as a guest of honor and speak few words about seminar. Welcome to you, sir.
I think already I tried to give the significance of this seminar. As I said, actually, Dr. Raj Reddy sir planned this workshop in order to make the faculty members to teach the mathematics oriented subjects towards security and other things. Recently we had introduced separately we tried to introduce a elective open elective with the quantum computing, number theory and cryptography, because there is a huge demand in the cyber security field. We wanted the interaction of mathematics with the computer science as an interdisciplinary kind of thing. Those courses are introduced in order to prepare the faculty member at our institution. He has been trying for the last 4 5 months. Finally, he could conduct a one-day workshop. This is not only useful because it is every institution, or as a, if you are a researcher, there is a huge scope for huge demand of mathematics in the field of not only in the cyber security or cryptography. There is a huge demand in the data analytics, data science is also there, even other, because all the recent AI and ML, artificial intelligence, machine learning models are mathematical models only. There is a huge demand. This workshop, I think, gives some initial direction towards learning of in that direction, and also it requires collaboration with uh, other computer science departments, or even mathematics departments also are offering these courses. Data science course is completely, most of the universities are, they are offering data sciences, data analytics. This may be a first step towards in that direction, where completely you will be moving from conventional mathematics to into a applied or research perspective, in engineering perspective. This workshop has laid down some foundation in the previous classes, and this I try to give, there is a use scope for applying mathematical knowledge for this security related thing. Similarly, the number theorem, morning algebra, those things are also useful for data science programs, and where we are supposed to, rather than teaching one or two mathematics, of 3-4 mathematics are to be specially with respect to that particular program. More number of mathematicians are required, specialized mathematicians are required who are experts in this particular domain, rather than teaching the same intermediate with a refined way, teaching the current mathematics in the intermediate way. So these courses, I request Rajreddy sir and other people offer these courses in third year, like third year or after second year, third year or final year, so that it will be useful to get more things from the research perspective, rather than offering these courses in the first year or third semester. So, and regarding the job opportunities, there are huge number of job opportunities. Regarding the research, huge amount of data is available. Earlier, for mathematicians, it is very difficult to trace their theorems, prove their theorems. Nowadays, huge computational power is available. As huge amount of data is available, where huge data amount of data is available, you can prove it in a better way. Your concepts or the algorithms may be foolproof this data may be useful. Not only this data, and also a lot of research is going on, lot of huge amount of data is being generated in the visual data, not only the numeric data. Also mathematicians will look into that direction. So that is another area, is computer vision also going to play a major role. For that also, there is a basic is your graph theory or your basic algorithms and other things are also there. So this workshop, I think, has given a direction towards that. This is what I wanted to share. Rajreddy sir.
Thank you.
Thank you. Thank you very much. Thank you very much, sir. Now I would like to call Professor M. Ganeshwara Garu to give the closing remarks of today's event and to propose vote of thanks.
Thank you,
Over
madam.
to
Thank you,
sir.
Shada, madam. Good evening, ladies and gentlemen. It is an immense pleasure for me to offer closing remarks and vote of thanks for this one-day national seminar. I would like to begin by thanking Sandhya madam, Chairperson, DNP, CBIT, Education Society, who has given us motivational words and spoke about importance of mathematics in the field of engineering and also giving us support throughout. I thank our principal, Dr. P. Ravindra Reddy Garu, for his guidance and intellectual direction offered, and also I am thankful to Chairman and Convener of Web Branding Committee. This seminar has achieved what it is set to accomplish. It has enabled to participants and many different applications of number theory and cryptography. I sincerely thank the speakers, C. Govardhan Garu, V. Srinivas Garu, and M. Swamdas Garu, who accepted our request for being the speakers at this seminar. I also thank our HOD, Dr. P. Rajireddy, convener of this seminar, for continuous efforts towards making this seminar a reality. And thank my colleague, Dr. P. Suresh, Senior Assistant Professor, co-convener of the seminar, for successfully interacting and coordinating the event. I also thank my department colleagues who have involved in making this seminar a grand success. I thank Nagajyoti Madam for our technical support. Ladies and gentlemen, it has been a pleasure being with all of you today. My sincere thanks to all the participants who accepted the invitation, spared the time, and actively involved throughout the seminar. I request all the participants to fill the feedback form, which is available in the YouTube live chat to get e-certificate. Thank you, one and all.
Thank you. Das sir, thank you.
Thank you. Thank you.
Suresh, close this.
Small